Hey, should be good now.
Okay, thanks.
Okay. Yeah, you didn't miss much. So a slide that I always put up for everyone to see, just basically what is PyHC, why is PyHC? This is a meeting that happens 2 times a year. For those who have been here forever, you know this, and it's open to basically anyone interested in PyHC and what PyHC has going on. If you haven't been coming to our biweekly telecons, you are of course free to come, and those are listed on pyhc.org under the meetings tab if you're ever curious to see what's going on in the future. As far as other meetings go, we had our summer school this year. We've been doing that bi-yearly, so every other year. And then we're also going to be at AGU. We have a poster session. I think it's Thursday afternoon. It should say on the site. Yes, Brent is nodding his head. We're good.
We lost the audio again.
I can't win today. Okay. Hey. So to be covered during this meeting, today is the most like presentation based day. There's going to be a lot of project updates. And then at the very end of the day, we'll have some talk about the heliophysics software search interface efforts, specifically with the metadata and controlled vocabularies. Tuesday, we're going to be talking through the FEP4, aka the PyHC tiering FEP, and doing some work on that. PyHC Rex in the HSSI, and then talking through PyHC interoperability. And then the last day, we'll look at the FEP issues, literally the issues in the standards repo, and talk through some of those. There will be voting for FEP 2 and 3, and then we'll wrap up. And in the afternoon is an optional hackathon session. This should be my last slide. So just if you're online, if you're not presenting, mute yourself. You can unmute for question period, of course. If you're looking for the documents for the meeting, you can find it all in the PyHC G Drive, which again is linked on the meeting page. For the general meeting notes, if you just go to tinyurl.com/gen-meeting-notes, you can help me take notes for the meeting and make sure we catch all the details. And then most Zoom sessions will be recorded, uploaded for later viewing. It should be recording right now. And findable also later on the PyHC YouTube channel. So, and I added a bullet point because there may be contentious topics tomorrow. Don't forget the code of conduct, AKA, please be a good person. That should be all I have. All right. We have Happy up next. John, did you want to go ahead and share?
Yes, I can share my screen.
Okay.
Send request.
Send request.
A request has been sent to share the screen.
All right, it should be allowed.
Okay. There we go. Does that look like the right thing?
I think so. Are you sharing it in presenter mode?
Not yet.
Okay. Oh,
Which one are you seeing?
presenter mode.
Okay, how's that?
Well, it looks good on Zoom. We're trying to figure this out in the room.
Hang on, let me try something else. I think it's the 2-monitor thing. Hang on.
I think you had it right, John.
You're right. It's just the room. Sorry.
Oh.
Okay. Try again.
Okay, all right, let me get back there. Okay, and then this, but then, okay. How's that?
That looks good. Thank you, John.
Okay. Thanks, Julie. So yeah, this is just an update on Happy, and I have a comment in the end on interoperability. And Happy, of course, is a team. It's not just me. There's a bunch of other people. These are some of the folks that have contributed to a lot of it recently, so they're on the co-author list here. So what is happy? We'll just give the 5-minute version. Happy status, current and future projects. There's a lot of things we got going on. I'll summarize some of them. And then, like I was emphasizing in the title, a suggestion for PyHC interoperability. So what is happy? I mean, it's been around for a while, so that's why I'm just going to give a short summary. But basically, happy is a specification. And it defines access to time series data. So by time series data, what we're really talking about is data that's not only representing, values over time, but it's only indexed by time. That's the only way to query it is by time range. And so the data itself, you think of it as a table. There's a time column at the beginning, and then there's data columns, and they don't just have to be scalars. You can have 1D arrays, 2D arrays, arbitrary arrays, whatever, strings. And there's a special kind of string that kind of like a subclass or whatever, that's URI. So that's the data itself. And then happy is really, it's an API for exposing that data over a server. So we have a huge pile of data, and there's that table format there below the data saying, yes, this is conceptually a table. And then happy is some kind of server interface where you're managing the request and response structure from the user, but not really a human user. It's supposed to be for software, hence the API part. So that's the fundamentals of how happy works. And then I wanted to just show how simple it really is. The actual API, it's very basic. So to get data in that request, you just have to provide two things, a data set and a time range. So here's a request right there. And you can see the parts in bold, but there's a server root, a data endpoint, and then the elements that the data endpoint takes, which I said are data set, start, and stop. There's other details for this if you want to add, but not really to affect the query. You can subset the columns, I guess, if you don't want all the columns. You can just give column names, but I'm kind of glossing over that. So, and then the response is just a stream of numbers. It's literally an HTTP response stream. It's just streaming you the values. So there's no, you don't get a file back. You're just getting literally a stream of content. And so focusing again on this data endpoint, that's one of the endpoints that a happy server must provide. And so there are other endpoints as well. Info, which is where you would get metadata for each data set. So in this example, the ACE MAG data set here, if you ask the info endpoint with data set equals ACE MAG, then you would get the metadata for that one. I won't go into the details there just because we're going quickly here. Then the catalog, that's the list of all the data set names at that particular server. And then capabilities and about, I'm going to skip over those today. Okay, so that's what happy is. What does it do? Well, the focus is interoperability, focusing on common access. And I've shown plots kind of like this before, but I wanted to emphasize it in a little bit different way. So you have data servers on the left, like a bunch of known ones, C2Web, SSC Web, there's the Virez server. And so they already have their own custom API. Each one has a different color custom API there. They have all also added a happy interface. And this is not a definitive list of known servers. I've got that in a minute. But then they all have happy, so you can get to them in a similar way. And then on the right-hand side here, there's various clients that all now are happy enabled, or they can read from a happy server. So the Python client, of course, that's why we're in PyHC. We have a Python client. We also have a Python server on the other side, but the focus of the work here has been on the client so far. And then there's other tools, PySpeedos, also in PyHC and Speedos itself. There's MATLAB, IDL, and R clients, Autoplot, and recently TopCat, an astronomy tool, supports it. So all in all, there's on the server side, there's maybe over 10,000 data sets. And a lot of places are using and adding happy to their own tools, and we don't even hear about it. So one of the things to emphasize here in terms of this interoperability piece is that if you make your data available with happy, you get all these clients for free. These tools can already start using your data. You don't have to provide a client for people. And then on the flip side, if you add happy to your client, you're instantly able to read all these different data sets. So that's just the whole point of interoperability, is to have this kind of common layer somewhere that means that everything doesn't have to be a one-to-one mapping. So this again, here's the list of the known happy servers and total data sets at each one. Don't want to go through this in detail, just to emphasize there's a lot of different institutions that are using this. NASA is one, the heliophysics, various heliophysics focused archives and data centers, and then some European folks as well. And then ESA and ESAC, the cluster mission data is available that way. And then some ground-based data like Intermagnet and SuperMag is coming. And here's some other ones that are coming soon. Things that are in yellow are in progress with a release date coming. And so on the horizon, some other folks as well. The Madrigal database in the CDAR community, that's a great big one. We're really excited about that. They're interested. It's just a question of funding and opportunity. And then the NOAA here in the middle, NOAA SWPC, the Space Weather Prediction Center, they've stood up their own happy server, but they're very cautious that they're going to do a lot of testing. They'll be releasing it in 2025, maybe towards the end of 2025. Okay, and then I won't spend too much time on this, but if you want to explore Happy and figure it out, there's the Happy Data Explorer website. And that's where the list of all known happy servers is. You can drill down into it, look at the data sets that are available and parameters, and it has code generation. So here's a quick example. Intermagnet is the happy server. The data set name is below that, and then you pick a parameter and a time range. And in this case, you've selected, oh, show me a script. How would I get this data? And it generates Python or IDL or MATLAB. Here's the code you would use to get to the data. If you're really just doing quick look, then you want to see if data is there, you pick image and it'll plot it for you, or you can pick data and it'll download it for you. But it's really meant to help explore. At each of these stages, it'll show you the URL that it used to make this call, and then you could paste that into your own code and get started with it that way. So, okay, this one's a longer example. I'm gonna skip it for now. And then the verifier, this is a way, if you've stood up a new server, it runs a whole bunch of tests on your server to see, does it pass, does it meet the specification? And when it does pass, then we can include it in our centralized list of known servers. You can run it locally or just over the web, point your server at it. Okay, happy status and future projects. So there's a lot of things going on with the happy team. So I'm not going to go over all these. Some of them are here just to document what we're doing. The ones in bold, I'll talk about in particular. One of the things that we've noticed is, since Happy deals with time series data, is that it'd be nice to know when different data sets are related. Say a server has a bunch of different data sets, different versions of the same data set at different time resolutions, like the highest resolution, 1 minute, 1 hour, 5 hours, whatever. Then it would be nice to communicate that to clients. Hey, these are all the same thing, just different cadences. And so one of the people who wrote a happy client, they did this already with a specialty way with their server so that their client tool could automatically pick the right resolution based on, say, what time range the user was trying to visualize. So we thought that's a great idea, and we're working that into the spec. We have a way of doing that. It's taken longer than we thought because it's kind of a general problem that you might want to link data sets together for other reasons. Maybe a data set also has a file listing, or you want to link the raw data to the calibrated data. So we've got something in mind for this. We're sort of fleshing it out. It's not exactly JSON LD, but it will map easily to JSON LD because the happy info response is not JSON LD, but we want to be able to represent what we have in there as the kind of linkages that you get with JSON LD. I'll just make a quick comment on fair compliance. Rebecca Ringett helped us do a scan through, and she pointed out some things. So we'll be adding like a license keyword using the spdx.org list of licenses and provenance. Okay, there's a lot of different projects going on right now with Happy. There's a caching mechanism that's being created. It works with any client, but the Python one is the one we're heavily testing it on. It's more like an upstream, like a proxy server. It will cache things, and that cache will be a generic one readable by the clients. And so there will be a poster on the AGU on that from Norberto Lopez at APL. There's an amalgamation tool I think I saw Sandy online. He's working on that. And local data serving, if you have local data, you want to show it in a Happy server, or you want to fuse data from different places. And this one we're excited about because Happy has, basic metadata, but a lot of what's in there could be used to generate a space record. So we're working on a Happy metadata tool that could generate space records. And then some projects are underway, but we have limited funding, so we're sort of just putting them out there. Hey, if anybody wants to work on something. And this one's in bold and red because I'll talk about it later. Generic plotting client. I mean, that's something I think we could talk about in the interoperability part. There is a plotting client available for a Happy server. I think would need a little bit of tweaking or some work to make it truly generic. It's a really nice timeline viewer from Ilko Doornbos at the Dutch Meteorological Institute. So just putting that out there. And the Helio Cloud project has some Happy-like features for its data catalog. And also we're putting some data in Helio Cloud that will be accessible via Happy. So we're going to be testing that out this next year. Some things that we're just thinking about in the future, if you have a more complicated query that's not just time range and you want to show the result could be still a time series table. You could serve that through Happy, kind of a results interface, or a result. You stand up a Happy server just to serve the results of a query. So not really stand it up, but you have one there and it's able to handle results. Okay, this one I'll skip over because I talked about upcoming data sets, but we do think about this a lot, trying to get and encourage other providers to adopt Happy. Can't really force it. All we can say is, hey, if this is helpful, we're here to help you adopt it, because we don't have any money. We do have little bits of money to show up and help you climb the learning curve. So there's some we're going for sort of near term, long term, other things we've just barely thought about, but that is something that we are pushing in the Happy team. The other thing that we're trying to do adoption wise is the International Heliophysics Data Environment Alliance is looking at a process by which they might recommend standards. So Happy that our team, we'd sort of volunteered, hey, well, we'll go first. There's no process for this yet, but we'll try to go through that once there is one. And it'll probably be patterned something after the International Virtual Observatory Alliance, the IVOA process. So stand by, see what happens with that. Okay, other things, I'm going to skip those for now. We are trying to come up with like a general way to see what all is available with Happy, maybe as a very, very simple search and tracking outages. So, okay, so this is the last thing I wanted to say. A suggestion, I'm just tossing this out there, see what people think. And so I'm suggesting, and the Happy team, we've talked about this, what if we could come up with a common data model for time series data? Just I was talking before about with Happy as a way to provide a sort of a sameness layer to enable interoperability where we don't have to have, one-to-one mappings. You go through a common access mechanism. For analysis and plotting code, the internal data model fits in the middle. It sort of isolates your data sources from your plotting tools. And then the adapters bring data into your data model, and then the tools don't have to know anything about specific data sources. So this is a common model. A lot of software packages in PyHC are using this model already. I'm pretty sure SunPy has something like this, and PySat and SpacePy. And so if we could come up with a data model that we could agree on for time series data, then I think there could be a lot more code sharing and even just concept sharing. So just some random thoughts on this, like what I said before, data model. It does isolate your data source from your analysis code. And then the plotting tools truly become reusable, right? They don't really care what the data is, just bring it to them in this data model and they'll be able to handle it. And the data model itself can be language agnostic, but then we would definitely need a single implementation in Python. And then everyone just imports that and we sort of maintain it together. And this is hard. So because we're even looking at now, how do we represent time? And that's created a lot of discussion already. So, and then you'd have to work on how we're going to store data as arrays, and we'd have to have flexible metadata capability. There's a lot of different metadata standards you'd want to pull in. And so I wanted to emphasize Happy is not this model. I'm not saying, hey, let's use Happy for everything. Happy would just be like any other data source. It would have to be mapped into the data model. But then the part that's exciting for the Happy team is, all right, then we're truly plugged into everybody's tools in a kind of native way because everyone's sort of committed to that data model. So that's pretty much all I had to say. I've got some more slides here. Oh yeah, this one. Happy is a chicken and egg problem, right? If you have a new standard, nobody wants to implement it on their server because, hey, no one can read this data. And no one wants to write clients because, hey, there's no data available. But we're starting to climb up this curve a little bit. And we're starting to see good adoption on both clients and servers. So we think we're getting there. And then there's plenty more info. I'm just leaving this in the slides. I don't want to go over this. There's some links about stuff. Tutorial notebooks are from the summer schools. That's the bottom link here. And then there's some demonstration stuff if you want to see how it works and try it out. And then finally, if you want to connect with the team, we do have telecons every Monday at noon, except not today, but because of this meeting. But then email us there or just, and we'll get you a link to the meeting and it can help you out. So that's the update. Happy to take questions.
There are claps in the room. Thanks, John. Do we have a quick question for John about Happy? Is there a question online? All right. Not right now. All right. Thanks, John.
Okay.
All right. Next up, it looks like we have Nick Murphy.
All right, can you hear me?
Yes.
Awesome. And attempt to share my screen. Showing up.
Yeah, it is.
Awesome, cool. Things are going well so far. So I'm going to give an update on Plasma Pi. And to give a very quick overview, Plasma Pi, the mission of the Plasma Pi project is to grow a fully open source software ecosystem for plasma research and education. So including heliophysics, laboratory plasma physics, high energy density physics, and fusion energy sciences. And if you'd like to learn more about Plasma Pi, I won't talk much about it now, but we have awesome online documentation on the World Wide Web, and I put a link to that in the chat. All right. So moving on to package updates. So very excitingly, we released version 2024.10.0 last month. And one exciting thing to note, besides that we went to date-based versioning, is that we have no number dependency for, and this leads to quicker Python 3.13 support. So Will Barnes is probably happy about this for Fiasco, but Numba usually takes a couple of months to be released on the newest version of Python. All right. We also put a lot of effort into updating and expanding our contributor guide, which is available on our documentation in preparation for the summer school. And this is foreshadowing since we're going to talk about the summer school in just a little bit. We also switched to the SRC layout, which is recommended by the Python packaging guide. And it turned out to be not that bad. There were a couple of things that caused a little bit of figuring things out, but overall it went pretty well. So src/Plasma Pi is where the package source code is, and we have a separate tests directory for the tests. All right. And as I mentioned in the spring, we've been continuing to add and improve type hint coverage. And since we just dropped Python 3.10, there are a couple of Python 3.11 type hint capabilities that we can now use. And I won't get into it, but we do have some new functionality for high energy density physics also, mostly from Peter Hoyer at University of Rochester. So one of the big infrastructure updates is that we switched our test runner from Tox to Nox. So Nox is a test runner and automation tool. So it's a package which we can use to define different testing sessions. So it helps us specify like what packages to install, what Python versions to use. And the most exciting thing about Nox is that the configuration files are written in Python. So we have a noxfile.py instead of a tox.ini file. And in my own experience, Nox is a lot more user-friendly than Tox. I was using Tox for several years, maybe 5 or so, or longer than that even probably, and still never really understood what was going on with that. But Nox was really helpful. And it also has some really nice aspects where you can dynamically generate sessions using all of Python's standard library. And it's also possible to parameterize testing sessions. So PyTest has the pytest.mark.parameterize decorator, and Nox has the nox.parameterize decorator, which is pretty helpful. Nox is also really well suited for automating tasks other than tests. So we have in our noxfile.py sessions for running tests, building the documentation, also things like validating our citation.cff file and making sure that we're not missing anything in manifest.n, and also things like adding type hints with a couple of packages like autotyping and monkey type, which are pretty helpful, but not quite something that we want in continuous integration. In the last couple of years, we ended up having a booth at the American Physical Society Division of Plasma Physics meeting. And this was really cool because we had a chance to talk with many students and especially early career scientists, and there was a lot of excitement for Plasma Pi. This year, I ended up giving a presentation on the need for workforce development for research software engineers in plasma physics, which is something that is also needed for heliophysics. And this is a little bit more foreshadowing. So one possibility, which I've brought up before, is should we have PyHC booths at heliophysics conferences? All right, so the highlight of the last 6 months is the Plasma Pi Summer School, which was a sequel to Plasma Hack Weeks that we hosted online in 2021 and 2022. We held the summer school at Bryn Mawr College from July 29th to August 2nd, and we were fortuitously able to support travel by 23 participants through an NSF award, through our NSF award. And this included a lot of undergraduates, including, I think, 2, maybe 3 actually, I think, from the PyHC summer school who heard about it there. And we also had tenured faculty, including a few from small colleges and one in Columbia. The topics of the summer school covered how to use and contribute to Plasma Pi. And this was a lot of work. And one of our main contributors has been busy building a balloon to fly in Antarctica. So we ended up bringing in Shauna Gordon McKeon to lead about half of the sessions, which are on more general topics like Git and GitHub. And Shauna is also an expert in a lot of open source things, but including open source governance, where governance is defined broadly. So she would be a great person for us to talk with. And we had a bunch of topics at the summer school. So I talked about Plasma Pi's origin story. And then we covered the code contribution workflow with Git and GitHub. This is something that Shauna covered. Of course, AstroPy.units. And then we went through a couple of Plasma Pi subpackages, including particles, formulary, and dispersion, which includes a lot of plasma wave dispersion relationships. We also had an hour-long session on psychological safety in code review. So psychological safety is the group feeling where you feel able to bring your true and authentic self into the workspace or space of learning. You feel able to contribute. You feel able to learn. You feel able to even challenge the status quo. And so we had a lot of discussion about that because it's really important and really hard, especially since a lot of code review is done text only over GitHub. We also talked about how to contribute documentation to Plasma Pi. And then because of a lot of Plasma Pi specific applications, we ended up giving an introduction to decorators, which surprisingly, I think went fairly well as type hints. And then with Plasma Pi applications, since we have some decorators like validate quantities and particle input, which are needed a lot to do things like write a plasma formulary function. On the last day, we had a couple of unconference sessions, and this was the first time that all except a few of the organizers had a chance to experience. So this was the first unconference for almost everyone there. We also had some hack sessions on the last day. So this was really cool. And there were things like an unconference on fusion applications, one on heliophysics, and then on a one unconference session was called Fun because the Olympic women's soccer thing was happening at the same time. And then we also had group lunches. So we ended up having like buffet lunch type things where we brought everyone together and everyone sat together. This is something that was actually our highest rated part of the summer school, which is not surprising. Everyone likes lunch. So for future PyHC summer schools, if there was a way to have to bring the participants together to have lunch as a group so that people aren't kind of on their own for lunch, which can be kind of intimidating. But there's some possibilities for future PyHC summer schools. So the summer schools that we've had so far in 2022 and 2024 have focused on how to use PyHC packages, which is really important. At the same time, I've been wondering, should we have a summer school on how to contribute to PyHC packages? And we really need Helio research software engineer workforce development. And this would be one possibility to move in that direction. However, this would be a lot of work, especially on like the PyHC organizers, especially Julie. So we really would want to reduce the lift for this, and with that, the chance of burnout. So we could bring in external trainers for the more general topics like Git and PyTest that most PyHC packages or all use. And we could also make use of existing resources. So NSF has funded a project called Intersect, which is producing a lot of training materials for research software engineering. NASA's transition to open science thing initiative. Also, they have a lot of materials. PyOpenSci is another great resource. They have a lot of open source guides. And then we also have a bunch of Plasma Pi summer school materials, which we could make use of. So the future outlook for Plasma Pi. Our current NSF Cyber Infrastructure for Sustained Scientific Innovation Award concludes in a few months. And we have a renewal proposal due on December 2nd. Hooray! Which is part of the reason why I'm not in Boulder this week. And we're going to include Plasma Pi summer schools in even numbered years. And we're also looking into additional opportunities like NASA's heliophysics tools and methods, which is due, I think, around February 27th. NASA's open source tools, frameworks, and libraries, which is probably due in June. And we're going to put more of our Helio and Astro focus in that proposal. And then the Department of Energy, we can look into for more fusion energy or laboratory plasma science, even high energy density physics possibilities. So with that, I will finish. Are there any questions? Feel free to put them in the chat also.
Do we have any questions for Nick from the room?
Can I ask one real quick? This is Sean here. I was just curious, what exactly is the difference in the source layout, the SRC layout you said that you switched to recently? I hadn't heard of this yet.
So in most PyHC packages, most older Python packages, so like Plasma Pi had a top level Plasma Pi directory, which is where the source code for the package was. And in each of those, there was a tests subdirectory for each subpackage. In the SRC layout, the source code is in src/Plasma Pi, and there's a separate top level tests directory, which includes subdirectories for the tests for each package. And the reason why the SRC layout is favored is that there can be a lot of subtle problems that arise when you have a top level directory that, so like, for example, if you're in the top level directory and you type import Plasma Pi, you could import the package without actually having installed it. And when that happens, you might run into some problems because some things might require the package to be installed to work. So it ends up being fairly helpful. And the Python packaging guide has a page on this, which I'll try to put in the chat, that goes into this a bit more. That's a great
Okay.
question. Thank you.
Yeah, that seems straightforward, but it's good to know that's the current recommendations. I'll keep that in mind.
Yeah, for new packages, for existing packages, not necessarily the best thing to change to.
I got a question, Nick. This is John B. online.
Please.
Yeah, okay, yeah, nice talk. The RSE development is interesting. I'm kind of interested in that too. So there's various organizations for RSEs, right? US RSE and so forth. I think you're connected to those already, is that right? Or
Yes.
okay, so that might be another resource we could try to tap into for some of the RSE development. And you're contributing how to contribute to PyHC. Is that targeting, because the users are different, right, than the developers. Developers are mostly RSEs maybe, or and then the users are mostly scientists. So I think that's something to think about as we consider your what you're pushing for that. Is who are we targeting? Are we going to target the scientists because they know enough code to get by, but RSEs need to know it more.
I would say targeting both. So one thing that
Okay.
one thing that can be helpful is to blur the distinction between user and contributor developer. So in AstroPi, for example, a lot of users are also contributors, and that's something which I'm hoping that we can emulate for Plasma Pi and then PyHC more generally. And USRC is definitely worth looking to. I'll put a link to that in the chat.
Yeah, they have their own annual conference now.
Yes.
So it collided with Dash, but next year we've deconflicted it.
Right. There's also a question in the chat. Could you briefly say what Plasma Pi does? So probably the best packages to look into, we have a particle subpackage, which includes plasma objects, or sorry, particle objects, which can represent ions and fundamental particles. And then we have a plasma formulary, which includes a lot of plasma physics functions. And we have a lot of diagnostics and particle tracker functionality also, which I was just going to the documentation for. And the move away from Numba is because it usually takes a while for Numba to support a new version of Python. So Python 3.3 changes came out last month, and Numba probably won't support it for a while longer. All right, should probably finish there. So thank you, everyone.
Hey Nick, really quick, would you be able to share your presentation on a Google Drive?
Yes,
All
I'll
right,
put it in the chat also.
thanks.
Thanks, Nick. If you have further questions, put them in the Zoom chat. We should probably get to the next presentation, but thank you again, Nick. We can throw them on Slack if you want instead. There was just already a question in Zoom, therefore. Check both, Nick. Sorry in advance. All right, I think SunPy is up next. I'm not sure. Will and Nabila, you tag teaming? Is someone doing? Stuart, okay. Oh. Okay. I'm so sorry in advance. Hold, please. Can people online see the slides?
Yes.
Okay, cool. Thank you.
And hear the microphone. Okay, this should be pretty quick. Wait, where's the mouse? I've got to put the mouse over here now too, haven't I? Okay. Just an update on what's happened in the last, I don't know, year or so. No, that's not. There we go. Okay. The main things that have happened are we released 6.0 in June. We've pushed our 6.1 release back a little bit. Well, we've pushed our entire release schedule back a bit so that we no longer try and do releases at exactly the same time as AstroPi, because that leads to a very stressful week for me. We've been working as part of our previous Stoffel grant on improvements to how we maintain all our collection of packages. We've done a lot of, we've finalized our overhaul of our governance, and we also got awarded an Stoffel grant in this round. So new things that happened in 6.0, we cleaned up our optional dependencies a little bit. We did some really fun stuff with what dates we use for our coordinate frames in maps, and definitely didn't get it wrong and had to do a quick bug fix to cover up our mistakes. We added new map sources to Fido and map for adapt data. Will wrote a new planar screen context manager, which extends the API for how you can make assumptions about how the sky is flat when you're working in 3D coordinates. You can calculate, I didn't even know we did this, but apparently you can calculate a rotation matrix between two splice frames, and general cleanup. We had 16 new contributors to our 6.0 release, which is pretty nice, but there's nothing like a GSOC application cycle to bump those numbers. 6.1, when it comes out in the next month-ish, the big thing, the biggest single things are the addition of the helioprojective radial coordinate frame, which has the south pole of the coordinate system at the center of the sun. So you have lines of latitude being like radially increasing angle away from the center of the sun, which can be very useful for certain analysis, and adding support for S3 URLs for directly loading maps and time series in their factories. Yeah, which came from the HDRL/Helio Cloud team, which was a very nice contribution, on which I have critically neglected reviewing because I've been very busy. and also various other helpers and tidy ups as usual. So the other big thing that we've been working on over the last, I don't know, too long, is our package template. So we have the Open Astronomy Packaging Guide, which is a very opinionated Python packaging guide, which is how to write and manage a package exactly the same as AstroPy and SciPy does it. Unlike the Scientific Python packaging guide, which is also something I would recommend you reading, there are no choices in the Open Astronomy Packaging Guide. You can follow our guide and end up with exactly how we like it. The big thing that we've added to both the Open Astronomy Guide and the SciPy package template, which is like a fork of the Open Astronomy one, is the use of a tool called Cruft to automate updates when the template changes. So we've got the SciPy package template now has all of the config files for how SciPy wants to do everything from CI to linting to everything else. And if we change something in the package template every week, the bot goes and opens pull requests to all of our maintained packages with all of the change to the config files. So the idea is when we eventually manage to get it all working is all of the SciPy repos that the SciPy team maintains will all have the same config and the same, like they'll all feel the same to work with. They'll all have the same style, format as everything. So it should ease both our maintenance and people developing on any of the packages because they should all have the same sort of experience. We mostly have this working now. We're now in the phase of just adding more and more features to it, like centralizing more of the config. But every Monday morning, I spend my time reviewing and closing like 10 PRs as it opens PRs to all of our repos every week. But the next big thing is the change to the SciPy project governance that happened a few months ago. Our previous structure was originally put in place in like 2012. We had a self-electing governing board who appointed primarily the lead developer, who had sort of executive authority to just get on with stuff over the project. As the project has grown, the amount of work in that lead developer role has grown, and the board became less and less involved in the day-to-day running of the project. So we worked on refreshing this, heavily inspired from the work that AstroPy did, adding a governance structure to their project. So we now have a self-electing group of project custodians who, effectively are the people who have voting rights for the steering committee and other roles in the project. The bar to entry for project custodians is deliberately relatively low, but as long as you have had, maintained some positive contribution to the project, you can become a project custodian. They then elect a 3-person steering committee, and then there's still the self-electing advisory board, or will be when we get around to resetting that up. The first steering committee election happened, and myself, Laura Hayes, and Albert, she ended up on so the steering committee will have elections for one position on the steering committee every year. And finally, we got awarded 3 years worth of Stoffel funding. These are the list of main things we've said we're going to do, which is cross-project, so all SciPy package, cross-project documentation improvements, including like an overreaching example gallery and general more documentation focused on using the whole collection of SciPy packages together rather than just them being individually documented. Major work on our SunKit specs affiliated package and the SunKit magX affiliated package, which is SunPy's fork / continuation of PFSSPy. if you were using PFSS-Py, if you're still using PFSS-Py, stop and use Sunkit Magics instead. You should be able to just replace your imports and carry on. The difference is it's actually maintained. There's also been significant improvements to the stream tracer package used by Magex. It's now fully parallelized, written in Rust, and faster than the Fortran version. And finally, we have a task which is just continuing general maintenance of the SunPy project. So that's it. Any questions? Stunned into silence. Excellent.
I got one. Yeah, this is great. I'm so glad you got that next OSTFL. And so that's always the challenge with great packages like this. That last item there, general SunPy maintenance. So do you have a vision for after this one, after this OSTFL expires? Are you going to try to just keep getting these, or do you have a long range plan? That's always the challenge. I know we face the same thing with Happy.
Yeah, I don't think there are many other paths to sustainability for like sufficiently niche science packages like SunPy other than continued grant funding. Because I can't see scientists on sufficiently large numbers donating money to the project or any other types of stuff. It's an ongoing challenge. NumFocus are helping us with it. But I think it's going to be grant funding for the foreseeable future.
Yeah, that makes sense. So, but kudos again for winning a second time.
Thanks.
All right. Thanks again, Stuart. Oh, joy. We're having some lovely Safari woes.
Yeah, no, you can see better than I can. Well, first
Yeah, it's fine. It's back over here.
Oh, I can see it backwards. Okay, let's try that.
Okay. The cursor on that.
All right, let's see. Okay, so just quick status update on SpacePy. Julie asked me not to give any introduction to what it does, so I presume most folks in the room do know that. If not, the summer school presentation is a good way to backfill. Oh, it's not on that. Let's try this one. Cool, now I can change it. All right, so 2 releases since the last time we met, but right after and then right before the meeting. So the big 060 release, big thing there was conversion back and forth between AstroPy quantities and pandas from our data model. This was the AstroPy quantities was for something Nick and I were starting to work on and then ran out of time. But hey, the support's still there. So if you have a CDF or any other SpacePy data model, you can bounce in and out of AstroPy quantities and pandas to the extent of compatibility. It's assuming the ISTP metadata. So if you, for whatever reason, have a data frame that you want to turn into a CDF, you probably do have to glue in a little more metadata to fill it out, but it's there. And then Dan threw a few more calculations into PyBats just in terms of dealing with the upstream IMF input. And then last Friday, in a blur of activity between myself and Steve, released 070. And really, this is spinning out. We had a 1-year support grant from NASA. So this is spinning that out. And this work was almost all my undergrads over the summer. So all of our NumPy 2 and Python 3.13 deprecations are gone. So you should be able to be running the latest version of everything and have it still work. So right now we're supporting 3.7 to 3.13. The really cool thing is James Westbrook went through and completely ripped out F to Pi. So we're still using Fortran, sorry. But that is being brought in as a direct shared library, which means that we don't have a build dependency on NumPy. It means we now are using the common C API, so we're not building a wheel for every version of Python. And it also means that when new versions of Python comes out, the existing wheels still work. And we checked performance on it. Some things it's like a 10% performance hit. Some things it's like a 10% performance improvement. So feeling pretty good about that. And that also meant it was easy enough that we're now making wheels for Raspberry Pi, because that's just fun. The other really big overhaul is we went through and just ripped through all of our docs. They all look kind of the same. It's a lot of the same content, but it's been totally restructured. So it's all auto summary based. So there's none of this, I put a doc string on it, but it's not showing up. Well, did you remember to put in the little tag to have it actually render? That's gone. And that also started our process, based on some stuff that folks have been promoting, the diataxis of separating out API and how to use documentation. So that'll be, it's really just groundwork, but that'll be rolling forward. And then we also went through and increased our test coverage, just trying to get that up to a reasonable thing across the entire, across the board. And so there was a few fixes involved in that. Here's just the numbers again over the past 6 months, a few hundred commits. Those are mostly the students and me. We managed to close out issues faster than opening them, so that's always fun. And again, we're continuing to migrate the support discussions, and we have those 2 releases, and we should be able to increase this release cadence now that we've done that big work to get rid of F2Py, because I swear every time I would cut a release, there would be something that NumPy would do slightly differently. Going forward, just real quick stuff. So this is promissory notes. Sounds like everybody else has been doing a really good job of getting their OSPL proposals in, which means we'll see if there's some left by the time I get to actually writing it. I was supposed to be writing that over the summer. It didn't happen. Big goal here is my students are all seniors, so I'm trying to get some freshmen and sophomores recruited, so we actually have some sustainability there, and particularly going through our local chapters of the Society of Black Engineers and Society of Women Engineers, so that we have a little bit more representation there. In terms of features, we're, as I say, eating the elephant of Conda Forge 1 bite at a time. Again, the F2Py removal is complete. That should simplify that. We're going to be switching our building to using Conda Forge instead of default, because that's sort of the first step in making sure we're doing that right. We'll package up the NASA CDF for Conda Forge so that we're not doing a bundle there. Has it been done yet? Or if it has, point me at it, because I did some looking and couldn't find it. The license is weird. It's not NOSA, but it's weird enough that it might be things. And then we'll start doing the actual build rules for SpacePy itself. I keep on promising we're going to actually get the spike of the data model adapters out, really. Still designing the cloud support. And Dan is still, should be writing this and isn't. I'm going to go back to the more positive stuff. So yeah, that's basically what we've got coming up. Again, if we can get to a point where we can be getting the funding on more than 1 year at a time, that'll help me keep some folks on board and keep some momentum going. But as always, pull requests welcome. And that's that, unless there are any questions. If you can't be good, at least be short.
So am I catching that you're putting SpacePy on Conda? That's exciting.
We are in the process of working. We have a concept of a plan.
Concept of a plan, yes.
Can we still use that joke? Is it too raw?
No. Glad to hear it. Hope it's not too hard.
Yeah, I mean, it's like I said, it really isn't eating the elephant thing. This has not been it hasn't happened because it's been a lot of prep work leading up to the point where we can start truly doing the job.
Hey, John, quick question on that adapters thing. Do you have time and funding and people to work on it? I'm trying to find a time when happy folks could support that too, because we got to the 80% place on that, and then the coordinating with the other packages is what slowed us down.
Yeah,
Not just you.
No, I've got quite a bit, and honestly, like time is probably the big thing, because this is not something that I truly need funding on or anybody else to do it on. That's honestly part of why we have that Pandas support. That was part of moving towards being able to go to and from the, This is part of being able to go to and from the SunPy time series was why that Pandas support is in there, which of course now SunPy's moving away from Pandas, but so yeah, it's honestly, if I get a few hours to rub together, I can make some progress on that.
Okay, when you're about to do that, let us know. We can try to think about it at the same time.
Excellent. Yeah, I've got some good stuff from Jeremy. So, and honestly, one of those things is that other funding kind of, even not having funding on this, if we have funding on other stuff, that helps because it means I can focus on this instead of something else.
Right. Okay, thanks.
So I was just going to ask, because here you're using from CDF, which is through, I suspect, through Pandas, right? Or is it through? Okay.
No, that's reading direct through PyCDF.
Okay. So, and if you go to your last slide, because you said you were packaging NASA's CDF. Yeah, there. To avoid bundling, have you considered using CDF lib instead?
It's come up, but the idea of rewriting the entire backend is not terribly appealing. That's, and we've also gotten some benefit from the fact that we actually are using the CDF library and are kind of bug for bug compatible. It's been really easy to add stuff without having to think about it. So Nick is pushing the idea of date-based versioning. I actually have no uncertainty about 1.0. 1.0 is going to happen honestly with that Conda release and the docs overhaul. It's a pretty clear and obvious bright line of where we're at that level of maturity. So we're close. I'm not going to wind up doing the LaTeX thing of being 0.9, 0.9.9, 0.9. No. I'm just going to read Bobby's comment. So CF license predates most open licenses, but should be open. Didn't change to NOSA since ideal map license. Yeah, I think it's actually better than NOSA. But the last time anybody looked at it seriously was the Debian devs looked at it like 8 or 9 years ago. And I think it was like Debian compliant, but not FSF compliant, I think. So it kind of depends on exactly what the Conda Forge guys think.
Thank you, John. All right. We'll just go to break 5 minutes early. So we'll have a 35-minute break instead. So we'll come back.
Actually, Julie, would it be all right if mine's pretty quick. Can I go through the PySat updates now?
Sure.
Is that all right?
Yeah. Stop share. You should be able to share. Did you want me to drive? I'm not sure if you put the slides up in Google.
I did not. I think I sent the request for sharing.
One second. Okay. You should be sharing now, but we're seeing Conda Forge instead. Hold on. Hold, please.
There we go.
There. Okay, we're seeing your screen.
All right, let me go back to the beginning. All right. Yeah, sorry, I kind of need to drop off early just for today, but I'll go through the quick PySat updates. We're just talking about some new versions we've released and a little bit of our roadmap. So this is sort of a collection of logos for some of the various library packages, and we've got the core team listed here. So I'll just jump right into the core package. Recently had an update, came out in October. most of the work was pretty small. A couple bug fixes. We got rid of a lot of deprecation warnings we were having with pandas, and the big thing to us is this transition to this spec 0 testing limits for maintaining back versions. So we've got our minimum supported dependency versions here. And we're actually now a little bit behind the spec 0 already because we were sort of on the cusp. So our minimum Python version right now is 3.10, NumPy 1.24, Pandas 1.5, SciPy 1.10, and Xarray we have in there. They use the date versioning instead of semantic versioning. And so we're a little bit behind, or I guess in a good way, we're supporting even older versions of some of these things. The big thing is we also have an operational environment, so we have to support sort of a much older Python version. We've been supporting 3.6.8 and NumPy 1.19 for a while now. Luckily, this operational environment is moving up, so we'll be up to 3.9 on our minimum, and then we're up to, I think, not sure if I had it here. I think we're up to 3.12 or 3.13 on our most recent, the most up-to-date versions. So that's the big thing on PySat is just we completely overhauled all of our testing to work for all of these versions. Going back, and then PySat NASA was a little bit more work on this release. It released at the same time, and we got a bunch of new instruments in here, lots of bug fixes, and a few features. So the instruments, we've got some of the more the in situ magnetometer and SEP instruments on Maven. We have the reach dosimeters, so there's a lot of those reach instruments up. The DMSBs.
The slides were not updated.
Oh.
You're still on slide 2 through the whole thing.
Well, okay, that's interesting. Thank you. Let's see if can you see the PySat NASA?
Yes.
Slide now. Oh yeah, let me know if that happens again. That was weird. So here's the list of instruments. Can you see the list of new instruments for PySat NASA?
We can see it. It's trimmed a little on the edges of it, but we can see most of the slide.
All right. So yeah, we've got the reach dosimeters and the DMSP SUSY and the Dynamic Explorer 2 data from back in the 80s. We've been using that with some comparisons to some of the newer VP instrumentation. And some new features. Some of these are pretty silly. There's this allow files to be unzipped after download. That was sort of, we had a piecemeal approach to that before, but it opens the door for a lot more of the compressed data. We've got some new concatenation methods for some of the different data types. We've got new cleaning routines. So the cleaning is built in on timed Groovy. And I'll just jump to some of the recent updates and what's coming up soon. So the space weather package should have a release coming up this month. PySat missions we're working on that one. And PySat seasons is going to be coming soon. That's mostly just cleaning it up because it's been sitting around for a while. And then PySat CDAC will have some fresh support for all of the Cosmic 2 instruments. Here are all of our stable releases that are currently available. So there's the core PySat, PySat NASA, PySat Space Weather, Seasons, Madrigal, CDAC, and our PySat CDF does have a stable release. But there's a lot of work happening on PySat CDF currently. And that's the current state of PySat.
Do we have any questions for Jonathan about PySec? Here or online? Not seeing any. Okay. Well, thanks
I
again,
was
John.
I'll ask something real quick, but I think we can come back to it. Just this idea of a common data model. I don't know if people had any reaction to that. I think most apps do have their own internal data model, and just
Yeah,
um,
that's sort of how ours works. Is all of the different packages are there, but they all funnel these different data sources into a single common data
right.
model.
So that's where I think interoperability wise, we could gain a lot of leverage if we could all find a way to
Yeah,
have
I
that
agree.
thing literally be the same piece of Python, that would be amazing. But it's a long-term goal.
Any
Are
other questions or thoughts
Are
on
you going
that?
to be, sorry, John, are you going to be, Jonathan, are you going to be part of the interoperability discussion tomorrow?
Yeah, I'll be there tomorrow for sure.
Okay.
Looking forward to it.
Uh-huh.
Okay. Thanks again, Jonathan.
Thanks
I
for
don't.
letting me go.
Yeah, sure thing. I don't think we have any other questions right now, so we'll go ahead now and go to break. You still get a little bit extra time. Come back at 11:10. Cool. Thanks, everyone.
So if checking your email isn't like entertaining enough during break, I did throw up on Slack a thread on what we might want to talk about standards wise on Wednesday morning, because we've got 90 minutes and I'm sure we've got about 6 hours worth of stuff we could talk about. So, hopefully we can prioritize what actually matters, and particularly what matters for interactive conversation. I told Julie I'd do it about 3 weeks ago, I think, and I did it 10 minutes ago. So sure, on top of it. Yeah.
Hey, Darren, you online?
Yeah, I'm here.
All right. I'm assuming you probably want to share your slides to Drive.
Sure, that's easier.
Yeah. But yeah, you can go ahead and share and take it away whenever you're ready.
All right, is that looking good?
Yep.
All right, I'll jump into it. All right, well, I'm Darren DeZeo, and I'm going to give you some recent updates on Komodo, our project there with Lutz that we're working on together. Let me be on the right page. There we go. So just the quick highlights of what's new in Komodo in the last 6 months. First off, there's now a verb model reader, and I'll give a few more details, updates on that. That's a great new addition. There's a new prototype Fortran to Python interface where you can actually, from a Fortran code, directly call into Komodo in Python, send it a query, get back an interpolated value and such. And there's a prototype for that. Sync and Yanko, the TSO5 model is a new tool that was added. It's kind of, again, as a prototype stage, just kind of to show that that's how that type of thing would be added. And we could add other magnetic field models or things like that going in the future. An updated web interface to some tools, and then lots of small bug fixes and improvements. All these packages do that. Weird things like IRI decided to change their model output format, and so we had to not only be able to handle the new format, but we got to detect which one is being written so that we load the right section of code to read that. And so things like that are always coming up, and those are the ongoing fixes and things that we're continuously working with. So the first one, the verb, the versatile evection radiation belt code. It's a diffusion model, which simulates the dynamics of particles in multidimensional space. And so it's got some unique features to it. It's a different type of model. Its coordinate system is not lat-lon, it's not XYZ, it's not things like that. It's dealing with L-shell, 88 back invariance, pitch angles, which is a very different type of system to work with. And so those required a very unique and custom way of handling interpolation methods and things like that, so that our standard utilities that we provide in Komodo, like flying a satellite through a model output and extracting values along the satellite path, will work. And so I want to give a great shout out to Sasha and Dimitri, who did great work on that, providing that code through a little bit of a sole source grant to do that. But they provided not only just the reader, but great documentation, validation notebook, plotting examples, unit testing, all that kind of stuff. So they did a great job with that update. So again, our Fortran to Python prototype, again, it allows you to call code directly from Python source. It supports, any of the queries you can make in and out of Komodo. And so they've tested, returning strings. It actually Fortran actually goes through C to get to Python, was the way they worked that out. That was, again, a small sub project that went through an Ensemble to prototype that work for us. It currently only works in a specific Docker environment, however, so we're working to generalize it further and try to make it eventually meet some of the functionality that another tool that we have at CCMC called Chameleon has been able to provide a Fortran interface. Unfortunately, Chameleon is an old code written in Java, and that's long been retired because just the support issues with that code was too much. The second Yanko model, again, we've added that model. It acts like a model reader, but it's actually doing all the computations and things on the fly, given what positions you've asked for, and so can do all the standard returns that you can get back from a second Yanko model. Again, it's developed as a prototype that we could use to develop future other tools that we could pull in and be able to visualize some of the gap space between ITM models and some of the magnetospheric models and get those field values in those regions of space. Komodo on the web. Again, we've got several models supported on a web interface to Komodo. So it's just a PHP page that's scripting calls to Komodo and Python in the back end. But it then ties into the CCMC run request system. And so all the runs that are available in the CCMC library for those models are then immediately available to be visualized online. The page automatically handles all the logic of adapting for various, variables, units, coordinate systems, that kind of stuff. It can generate 1D, 2D polar, and 3D plots. And each page that you look at actually can generates a link to a short Python code that was used in my script to generate the plot. And so if you actually have the model output on your machine and pull that script in, you actually get the exact same results on your own computer and then fully customize it to your heart's content beyond that. So it's kind of a way of making that available to people as they go forward. So the most recent updates to that in this, we've added the SWMF ionosphere output as a new output source on the web page. We've improved a lot of things on the plots. 2D polar was a new feature that we've added just in the last week, actually. Turns out that while we're using Plotly for all our visualizations, Plotly has no native spherical coordinate system in its tool belt. So we gotta do some special things to support the polar plots. And while doing that, we actually augmented it a little bit to take advantage of our coordinate system conversion that's available in Komodo. And so now when you request these plots in 2D or polar or 3D, you can choose the coordinate system you want to display it in. So even though a model might be executed and their output is in SM coordinates, I want to look at the output in geographic coordinates. That's just now an easy checkbox to do that. And then also little things like, centering contours around 0 and things like that. So just to give a quick update on how that looks on the web, just on the CCMC website, you look at the model name. There's a list then of all the runs. So for GitHub, there's 706 GitHub runs on a request in the system. And you can actually click and go into the plot and visualize that run output. This is now a view of the SWMF ionosphere output and looking at a polar plot and what that looks like. And again, the SM output is in the coordinate system of the model is actually SM coordinates. But again, from the bottom here, there are pull downs. You can choose which coordinate system you want to display it in, and a lot of various options for how you plot it. And then on the right is that sample Python script that just sets a few variables and calls a couple of little functions that generate the plot and save it to your disk for you. And so again, with this online tool, we can now generate analysis and extractions at various heights and positions, and generate 1D, 2D, 3D visualizations for in the online tool that you can do. Obviously, all these things and more are much more available in the full Python package, but the online tool gets you a lot of the most commonly used functionality. So where we want to go with this, we're working to bring Python support up to version. We're at jump right now, but we're aiming for 3.12. We higher if we can. Currently, it's only the 3.10. We've got some older pieces and some dependency libraries that are not fully up to date either, that we're working to work around and bring things up to speed. Working on updating our documentation and unit testing. Again, some of the sample code that we got from Sasha was great for that, for giving us some good examples for unit testing, and we're going to work to upgrade that. We're looking to add a field line tracing functionality, a generalized tool that will work within all of our supported models. And then the last one is kind of a bugaboo a little bit, but the pip conda forge updated, and that that IFF is not a typo. That's old math for if and only if. We could figure out a way to include C code in a pip upgrade. And every few months I do a little more Google research and try to figure out a way. I've never been successful at that. And so while there is a version on pip, it is out of date, and we're not really anxious to update that because it can't include all of what Komodo has. And we want to actually have all of Komodo there. And so we're trying to still find a way to fix and find a way to work around that that gotcha. So that's the end of what I have.
Any questions in the room?
Darren, C is fairly easy. Just can you just shoot me an email with like where you have a non-pip way of building it, and I'll try to do something for you.
Yeah, I'll get in touch with you. Hopefully we can get this cleaned up. And
Yeah,
it's
I
kind
think
of
I've
a
got my head
long-standing
pretty well
issue for
wrapped
us.
around it now. So
Yeah. Okay, that'd be great. Thanks.
cool.
Yeah, thank you, John. That would be a big help for me and lots of others.
Yeah, hi Darren, this is Will. I was going to say something kind of in the same vein. It sounds like John maybe already has a solution, but if you haven't looked at PyBind 11, it's a pretty useful solution for like doing C Python interop. And then there's a lot of, I think, honestly, relatively new tooling around building wheels for if you have a fairly complicated tool chain, and doing that on CI as well. It's gotten a lot easier in very recently. The other thing I was going to say is if for field line tracing, we maintain a tool for doing field line traces through mostly magnetic field extrapolations, but it's general. You know, it's basically works for if you have a vector field, like a volume of vector field, then it will work. It's called Stream Tracer, so it might be worth seeing if that's a viable solution for you all as well. And it's written in mostly Rust, so it's really fast. And you can talk to Stuart more about that.
Okay, thanks. I'll look into that.
Do we have any other questions in the room? Okay, you have a couple in Slack. I'll go ahead and read it out for you, Darren. So regarding the Komodo web output, has there been any discussion regarding customizations of those plots as well as user interactivity?
Customization of those plot right now, that's again, it's whatever features I can add to the web interface between the two, right? And so I'm writing PHP that works and then generates a Python script in the back end. So further customizations really means if there's a feature that you want to add, I would have to add that to the web page as a new pull down or a new option. So everything is possible. It all just depends on user feedback right now. If somebody has something that they're very interested in, it's not hard to add those to it. It's just I can't have an open box that says type in what you want. That doesn't meet NASA security to say, here, type in some extra few lines of Python and it'll go and add this little customization to it. I can't do that. I have to do, security checking on inputs and things like that. So, but again, we can add any features that are requested.
Some thanks. And there's one more. Some people have noted that the examples in the Komodo CCMC documentation aren't working anymore. Is there any effort to test that documentation routinely and maybe fix what's broken right now?
Yeah, that's currently on my to-do list, is to go through all those again, because things do change over time, and that's something that we're hoping in the next very short term that I do a complete walk through all the examples and test on myself and fix all the little good glitches that have showed up and accumulated over the last few months. But I'll definitely take a look at those.
Awesome, thanks. I don't think there are any more questions right now, and we're at time, so thank you again, Darren. All right, give me one moment and I'll get the PySpeedas presentation up. We looking good online? Cool.
Okay, hi folks, I'm Jim Lewis, lead developer for PySpeedS, and I'm going to talk a little bit about some recent updates and our plans for the future. So I won't belabor this, but for those of you following along who might not be familiar with it, it's a successor to IDL SpeedS ported to Python, and we can load data a bunch of different ways, give you ways to analyze it and plot it. Plotting is based on matplotlib. And the current versions of PySpeedS are version 1.7.0, about a week or two ago. And the plotting part of it, PyTplot MPL temp, which I'll come back to in a couple minutes, 2.2.50, also in the last 10 days or so. And this is a result of a typical PySpeedS workflow where we've loaded some geomagnetic index data and some MMS instrument data and plotted all of it on a nice summary plot. So what's new? We have worked a bit on our environment dependencies. We now fully support NumPy 2.0, as do all our dependencies. As far as Python versions, Python 3.9 through 3.12 are tested and supported. For Python 3.13, some of our upstream packages are not quite there yet. For example, netcdf4 is a little bit difficult to install at the moment on certain platforms. So we're not going to claim Python 3.13 compatibility until we can sort some of that out. Let's see, in terms of plotting, there are a lot of missing plot options that were just sort of stubbed out and not fully implemented. So we're working our way through those. Those work a little bit better now. We've improved our handling of, we have this ability to make pseudo variables where you're just referencing maybe a group, several other variables that you want plotted together in a single panel. So that's working a bit better now. We had a user request to be able to plot symbols with error bars, but without the connecting lines. That turned out to be a little tricky, but we can do that now. And then probably the most noticeable one to users is we've made some efficiency improvements in rendering spectrogram plots. And that caused us quite a bit of heartburn at the summer school, actually. And I'll show you, I'll talk about this a little bit. So quite often when you're plotting spectra, you have time varying bins. And this is a particularly hairy case where no two of them seem to have exactly the same bin boundaries. And so what we were doing is like sub-sampling in the Y direction on like pixel resolution. And that was blowing up the memory consumption, and it was blowing up the time it takes to render a spectrogram. So we implemented a little bit smarter algorithm where we make one pass over and get all the bin boundaries, and then we make another pass and sort of fuzz them out a little bit, because sometimes you end up with tiny little slivers, and we take those out and make sure that we render them properly, taking the fuzziness into account. And that was a quite drastic reduction in memory requirements and plot time. So before I think our Helio Cloud instances were allocated, I think something like 12 gigabytes of memory, and we were running out trying to do an MMS summary plot. And now that's for MMS, I think maybe for all spectrographs, I think it's basically at least an order of magnitude, maybe 2 orders of magnitude, less memory and faster rendering. So hopefully that'll be a welcome improvement. Some other things we worked on in our analysis tools. Some users reported issues with handling of NaN values. And so we found a few places where we needed things like NumPy NaN mean instead of mean, or NaN median instead of median. And that prevents the NaNs from sort of spreading out and contaminating the rest of your outputs. There were some problems being able to generate particle products from some MMS and ERG particle data, and we were able to fix that up. So now I think all the particle instruments on ERG are supported in terms of making spectrograms and moments and those sorts of plots. We also contributed a few bug fixes to the GeoPack library, which is one of our upstream dependencies. And that's a pure Python port of the mostly the Sigonenko Fortran-based libraries. So we've done a fair amount of vetting. They seem to match the IDL results we're getting very closely now. So we're glad to have that straightened out. In terms of load routines and CDFs, again, some users reported some issues with time clipping when you're downloading via CedaWeb. Like I think there's like one mission, I think it was New Horizons, that actually has the entire mission in one single CDF. And so that we never expected to have to time clip on that scale. So we worked that out. That's working now. Then there's some other issues, I think, with Maven and maybe some non-CDF data types where if you're loading multiple files in one operation, the data from the different files wasn't quite getting merged properly. So that should all be straightened out now. We added load routines for quite a few more geomagnetic indices. So some coming from NOAA, some come from the Kyoto World Data Center. There's a server in Germany that has some of them for some time ranges. And those are important, not just in their own right, because they're interesting, but some of those like SimH, for example, that's an input parameter to some of the GeoPack field models. So we definitely needed to have those included, and those are there now. And then every time we expand our support to new missions or new data sets, we find weird things that are going on in the metadata, and they're technically not ISTP compliant, but when we find these things, we do try to make sense of them wherever we can. So that means there are a few more ERG and cluster data sets that could be loaded successfully now. And then as we expanded our testing to NumPy 2.0 and Python 3.12 and hopefully soon 13, we did find some pending deprecations in some of our calls to the upstream libraries. So as far as we know, the latest versions of PySpeedS have resolved all of those. So we're hopefully ready to go when our upstream packages support Python 3.13 and beyond. One big thing we've been spending a lot of effort on is working on our packaging and organization. We're trying to align ourselves with the PyOpenSci recommendations. So the most recent one we've done is we've migrated away from explicitly calling setup.py, which is strongly discouraged now. And now we have a pyproject.toml with setup tools as the back end. And we're eventually going to move to PDM as the build backend, and that will hopefully turn out to be useful in case we ever decide to include some C code or other languages in there. We've reorganized the namespace a bit. It was getting a bit cluttered, so we took all the mission-specific packages like Themis and MMS and ERG, and we pushed those down into a PySpeedS.projects namespace. And then we're also importing all the PyTplot routines. So if you do import PySpeedS, you get all the PyTplot stuff under that namespace. And we put in some kind of gross hacks to make it backward compatible for now. But there are some caveats with that, and those are not going to stick around forever. And I'll come back to that in a minute. been making a big push to improve our documentation. We got a lot of that done in time for the summer school, and we're still pushing our way through some of the other areas and trying to make our read the docs pages as complete as we can. And also we went ahead, we were missing a lot of release notes for prior versions of PySpeedS. So that's sort of a hole in our release process. We weren't keeping those up to date. So we went back, and now if you go on GitHub, you can see at least a summary of the changes for the past releases. And we're kind of happy that in terms of our QA and testing, we recently turned that badge green, and we've got over 90% test coverage. So that's encouraging, and we're still working on that. So upcoming changes, biggest one is we're going to put out a PySpeedS 2.0.0, and that will have some breaking changes in it, thus the major release number bump. It's probably the biggest part that will be noticeable to users is we're going to completely absorb the PyTplot MPL temp package. And that was an ongoing source of confusion because there's this older version, a Qt-based version that is actually named PyTplot. So a lot of people would see like import PyTplot, and they'd say, oh, I better pip upgrade PyTplot, and then they'd get the wrong package and completely break their environment. And so working with Brian, the maintainer of PyTplot, we decided it would be best if we just folded that stuff into the PySpeedS package. And so that will be coming in a few months. We didn't want to put that out right before AGU. So sometime early next year, that will probably come out. Now, I mentioned we did do some backward compatibility hacks in terms of like managing the module, sys.modules stuff to make things available under like PySpeedS.themis instead of PySpeedS.projects.mms or .themis where it lives now. And the trouble is that that's a runtime thing. And so your IDE might complain about that if you have the old style imports. Even though they work fine at runtime, they're using static analysis usually to try to find those imports. And that can cause a bit of a problem at, code editing time. So those backward compatibility hacks will be coming out in PySpeedS 2.0. But we have a lot of code examples and tutorials out there in the wild already that are doing things the old way. So we need to make a pass over all those, make sure we're doing the imports the new way, everything under the PySpeedS namespace. And then we'll think about actually putting that release out. And we are working on a PySpeedS 2.0 migration guide that is now available on the landing page on PySpeedS.read the docs. As I mentioned, we're going to eventually migrate to PDM as our backend build system to accommodate any like cross-language stuff we might want to implement in the future. And we're also eager to get this released on Conda Forge, but again, particularly Geopack is not there yet, and we were working on that a while. It got sort of shelved, but hopefully we can come back to that soon. And we really do want PySpeedS to be available on Conda Forge. And then finally, we do want to implement some field line tracing routines. There is some code for that in Geopack. It's missing some features from IDL. For example, I don't think you could do traces out to the magnetic equator. You can only go to the poles. And then there are a few improvements that are in the IDL Geopack that are not in the original Fortran sources. And we're hoping that the maintainer is going to fully open source this at some point, but right now we don't have access to source code for those improvements. And so we might end up having to roll our own field line tracing, probably something based on the SciPy RK45 integrator. But I am interested to hear that Komodo might have that coming soon. Or so we're going to give some thought to whether we want to continue depending on GeoPack, or if we want to take some of these from Komodo, or I think SpacePy actually has some of the Sigonenko models in there. So that's something we'll be looking at in the future. And then we do want to include some better support for non-time series plots. It's doable right now if you want to pull the t-plot variables apart and do direct MATLAB calls. But as we found out in the summer school, that's kind of awkward and hard to teach. And we have that, we have plot routines for doing that in IDL SpeedS. And so it's going to be a fairly high priority to get those implemented in Python. So we could do plots like this, where here we have Themis, MMS, ERG orbits, and a couple of magnetopause models. And we would like to be able to make a plot like this in just one or two calls, rather than having to do a bunch of faffing about with matplotlib. And that's all I have. So any questions from the room or on Zoom?
Do we have a quick question in the room? I know we have a couple on Slack. Okay. Oh,
well, yeah, just real quick. Did I catch correctly that the PyTplot package is just going away now, and it's just going to be a
We'll
part of
probably do
PySpeed?
like a final release of them with some notes. Like if you import it, that'll point people towards PySpeedS.
Okay, cool.
And we will keep the, there might be some people still relying on the Qt version of it. I think, Maven might be using that. So we'll probably do the same thing, release a version of that one and say, if you want the old Qt plot, try this other package. So people won't completely get the rug pulled out from under them.
Yeah. Well, cool. Glad to hear that whole thing is finally getting resolved, because it has.
Yeah, and that should make it a lot easier to maintain the PyHC environment.
Yep. Yeah, good stuff.
One less thing for Brian Harder to have to focus on too. Okay, so for the Slack things, I have a cheeky question of will PySpeedS get its own logo soon that you can answer later? But to the real questions. So regarding all of this change and version 2.0.0 coming, how tied to the IDL-based SpeedS are you in development these days?
We're still going through IDL SpeedS capabilities and trying to port as much as we can to Python. So, so as I mentioned, like the field line tracing and the like XYZ plotting, as opposed to time series, those are high priorities. And then sort of the next set of priorities is probably to, like I know that in IDL SpeedS, you could do a lot of Themis calibration on the fly from the lower level products to more processed products. And barely any of that has been ported to PySpeedS. So just for Themis support, that's something we're eager to have. And then after that, it's just more or less whatever the users are asking for.
Makes sense. All right. The next ones look a bit more like comments potentially. So there's a word of caution for depending on Komodo. Komodo, both Komodo Core and Komodo CCMC has a NOSA license, which would cause problems with the PySpeedS license if added as a dependency. So maybe just something to keep in mind. And then Brent also managed regarding orbit plots. He suggests that we, i.e. you two, talk offline regarding this. He's on a grant to work with PySpeedS to bring some new plotting capabilities to supplement PyT plotting.
Awesome.
Meet each other at lunch. All right. Thanks, Jim. online, we good? Okay, cool.
Okay, so this will be a little bit different as it's an introduction, and I'll mix up my science because I'm a scientist in it. So hopefully you're gonna bear with me. So I'm a long-term postdoc, and I came to the US to tackle a kind of a problem that was developing, as in we didn't have proper analysis software to tackle the inversions of the solar magnetic fields. And I'm talking about the corona, where we usually don't measure this. And I've been working for some time on developing this package called CLEDB, and it gives a physical interpretation for emission lines in the corona and tries to invert physical properties out of them. So one thing is that I spread a lot of AI-generated content over the presentation for giggles. So you can convince Gemini to draw a corona, and it looks like that, apart from the pencils, because you can convince Gemini not to put the pencils for some particular reason. But the point that's there to make is that that's an image because we don't actually know how the magnetic fields look like in the corona. And up until a month ago, we never measured this quantity. So why? Just a few words about why this is important. We're usually a space-based community, and that makes sense because there's a lot of duty cycle and a lot of opportunities for synoptic observations when going into space. So a question that I always hear is, why do you bother with ground-based observations? And the main aspect of them is you can just augment it, the space observations with very punctual observations and try to make them better, but that's not all of it. From the ground, we can build bigger and more complex instruments that space doesn't really have access to because of both volume and cost. And we can do way more in this. And this is the problem why we never measure these coronal magnetic fields up to now. We don't have an established way of doing it from space because it's too complicated. So ground observatories are currently, are since last month currently the only types of instruments that can measure these things. And it's important to connect to to space weather phenomena and satellites and like solar orbiter and Parker Solar Probe. This is our missing link from the solar photosphere up into the space. And another thing is that we are used to diagnostics at high energies in ultraviolet, X-rays, and so on. While from the ground, we actually go to lower energies because we have way broader lines and they're way better spaced. So you can do individual line diagnosis as opposed to space where you get a bundle of them and then you make a response function using theoretical calculations and you hope that response function actually works. While here can actually measure individual lines. And we go to the infrared because that's the best atmospheric transmission window from the ground to not deal that much with the atmosphere, but that's a complication. So that's the technical basis of this. Now, what is CLEDB? I made something in a very newbie and unprofessional way, but I started to read as much as I can about things. So my main goal was to not do ideal, which I succeeded mostly. I was trained as an ideal user, as a PhD student, and now I don't have it installed. So I'm very proud of this fact. And it's mostly Python, and I'll get to that. I parallelized it the best way I could, and there are problems, and I could do better. And I have a GitHub repo that's available for anyone for it. And I managed to squeeze my way around finding some support from NSO, HAO, DKIST, and really grateful for some NASA grant that actually let me do the augments and that I want to talk about today. And this package will hopefully enable our community to interpret these novel observations that just got released, like UCOMP from the Mauna Loa Solar Observatory and the new Dikist observations. And that's its goal. So what does this do? It's the whole algorithm is based on 3 big modules. We have a build module. We need data. The problem is too complicated to actually solve analytically. So we do forward calculations, build databases of potential solutions that match observations, and then match those databases to the solutions at the end. So the first module is something that uses forward calculations to build a database. And you see the main problem there is that it's Fortran, sadly. When I started doing this, the only forward synthesis tools were in Fortran. And the worst part of it is that it's Fortran 77. And the even worse part is that the releases are given through tar archives over email to the people that the lead developer knows are interested. So I kind of convinced him to let me make a GitHub repo. So now at least we have the source code available. Progress. But that's a problem that I actually solved recently. The second part is preparing the observations and the databases so that they can be meshed. And that has a lot of caveats, and we'll go through that. And then there's 2 branches of analysis. You either have observations in 1 emission lines or observations in 2 emission lines, and you get different products out of it. And the first, so common to both, is a spectroscopy product that gives you the main physical parameters that you can find in the corona, like line intensities, Doppler shifts, line widths, and so on. Then there's a line of sight projected magnetic field submodule that just does a projected magnetic field inversion. If you have just information, from 1 line. And then there's the big inversion module, that submodule that actually performs a fitting between the database and your observation and try to give you a full 3 component in Cartesian vector magnetic field out of it. So if we go through here, this was the original database building tool, and it's a mixture of Bash and Fortran, which is plus static atomic parameter files and so on. So the only thing here is that it's a mess. And what I did was just use the simplest possible. This is still a complicated code. And it takes a long runtime to do anything in terms of hours, days. So I parallelized it the best I could and just spread the calculations using bash script in as many processing cores you have, and it just runs, and you scale the time based on how many processor cores you have available. It's not ideal, but it is what it is. But at the end, you get databases, you run those databases for each ion you're interested in, and so on. And the problem with that is that you had to, I'm not going to spend too much on this, you had to cycle through 11 parameters. With clever stuff, you can only cycle through 4, and then you get databases of 1 billion entries each. And that made the entire code be very hard, next to impossible to match or do anything, because that was extremely slow. So I spent the first part of this year, I got the opportunity to actually improve all of this. And PyKelp got released, and PyKelp is a forward synthesis code like the Fortran one, but now it's written fully in Python by Tom Shad. I switched that entire build module from CLE to PyKelp. I got rid of the Fortran binaries, and that's yes, which I had to build for a number of systems and architectures. But I got rid of all of those things, and now I can have a nice Python package that has a PyPy release, and it's just import it, and I can compute databases. And you also need to import the Chianti atomic database, but that again has a Python interface to it. You have to download it, and then you can import it from a Python interface, and that's also good. So I kind of cut down all of the reliance on Fortran code with this. And there's a slight difference in how these things are made, and that there's a discussion about physics about this, but I'm not gonna get into it. But the idea is that now I also reduce the databases to just a couple of 100,000 solutions from 1 billion. And that makes the entire algorithm work fast now. And so the idea with this, the pre-processing has separate modules and functions. The best I could understand on how to drive an architecture like that. And it just takes all of your data with using a set of constants and controlling parameters that are universal. And then this drives this entire flow chart of algorithms that process your data to get physical outputs out of it, and then get it ready to process. And there's an entire thing on how to read the data, the databases, how to match them, and there are some efficiency issues here, and there's a way of pre-selecting a minimal amount of databases that match your observations and so on instead of bringing them all. But okay, then there's the analysis module, and then there's those three submodules. The spectroscopy processing that gives you full outputs in terms of spectroscopy physical observables, the line of sight processing, and the full database matching. And then there's an intermingle between these things and these products in order to try to reduce and speed up calculations and so on. So at the moment, with all of these modules, I speed things up by Numba, and I'm getting the idea today that Numba may not be the best course of action. I do have an alternative way that I now am proficient enough to use, so I'm gonna switch everything from Numba to just using multiprocessor pool threads, and I'll see how that goes. Numba has been a pain. I might still use some ng decorators to make some functions very fast, but if you want to talk to me and convince me I should just quit Numba altogether, please do, because that's the idea I've been getting today. And I think I can live without it. I'm not 100% sure, but okay. So this is an example of what you get from a simulation of products. Won't spend much of this because this is mostly scientific products, but just to show an example. Now what I'm working on is to actually make an ingestion function for all of the new data sources that just appeared this year, like cryoners. And this is what comes out of this algorithm if you process raw cubes of tens of gigabytes of spectroscopy data from cryoners. And it's looking promising. It's in the work, and that's what I'm currently working on getting all of these individual instrument injection functions ready, because there's absolutely no coherence between keyword systems and so on, so that I can build an all-around wrapper. So each data source will probably have to have its own wrapper to ingest, but that's the best way I could do it. Then another thing is, and I'm not gonna spend much time on this, it's I've just implemented a new function that can process incomplete observations. And then there is a way of recovering meaningful magnetic field products in the absence of one polarization component. And there's an entire flowchart on how to do this, and this has just been integrated over this summer in CLEDB. And it seems to be working well. I need to validate it from a physical point of view, but the code distribution now has this capability. I made the documentation again to the best of my ability. I understood Sphinx was best, and I've done a manual Sphinx by myself. I now know there were better ways of doing than this, but there is something, but I don't have. So it's kind of manual. I made the files for each thing instead of using doc strings and make them comments, which I am gonna change soon, but slow. Whenever I can do it, but it exists. It lists them. It lists the functions. It lists the variables going in and out of each functions, data dimensions, and what everything does. So I hope it's useful. And Last thing is about the standard adherence, which I've been trying for some time to do. So now I'm 8 out of 15. And then there's something that I would call partly compatible, but I'm guessing if I talk to you people, you're gonna give me a slap on the wrist and make me do it better. But there are some that I think are fairly compatible, either based on how I implemented them myself, and I can find caveats of people saying you didn't do it right, or that. But what I need to do now is, after I finish with all of the code updates and putting and switching from number parallelization to the multiprocessor thread and having all of the data ingestions ready, I want to actually focus on doing unit tests for each of the submodules, and then actually having a release, and then figuring out how to do packaging, which I have no idea how to do, but slowly. But this is where I am, and hopefully by next year I am gonna get to 15, but hopefully. So the summary is that I kept developing this package for a number of years now, and I keep adding new stuff, mostly on the science side, but now I'm trying to ramp up on the software side. And I would like to know what I'm doing good, what I'm doing bad, and other stuff like that, so that I can actually try to make this a PyHC compatible package and start working with the community. And this is it. Thank you.
Do we have any, that's loud. Do we have any questions in the room? Or the mic end up. There.
I got you. Yeah, this is really cool. I have a couple questions. Maybe we can talk later too. But how are you getting at the Chianti data?
You download it locally, and then you have a Python module to just read the locally downloaded the database, the atomic database.
Okay,
And that's it. It's one import, and then it's stupid technically. You also have to set up an XUV top environment variable in Python.
Oh, this is using Chianti Py to do.
It's not even. It's kind of circumventing Chianti Py.
Okay. Okay, so this is like you wrote your own like wrappers to.
Not even that. It's I can show you exactly how to do it.
Okay.
But am I actually importing Chianti Py? I don't even remember. But I'm not interfacing the database through Chianti Py. It's simpler than that.
Okay. Okay. And then with regard to the parallelism or the sort of number versus multiprocessing thing, I would say, I mean, it depends on what you need to do. If you have stuff that's like really a bunch of nested for loops in Python, that's typically where I've seen Numba be the best use case, that it just is good at speeding up that type of calculation. But if you have sort of this more, embarrassingly parallel type of workflow, which it sounds like maybe you kind of do, or where you have tasks that sort of depend on each other and need to wait on like 10 tasks before you do like the next one task or something like that. I would also say it might be worth looking at Dask, which is a tool for doing parallel. It's a really powerful tool, but it's good for sort of parallel processing, and it can use different like engines underneath the hood. So it can use multiprocessing, or if you have some more complicated way of like scheduling tasks, I noticed you had some like Slurm stuff in your repo. You can use it on top of like an HPC job scheduler as well. And then like all that, your like top level code stays the same. You just kind of swap out like the configuration for how you set up the cluster, and then you send work to that cluster.
Ooh,
yeah,
okay.
So that might be a good thing to look at, but we can talk more.
Yeah, the Slurm came from the original requirements that they should be used in a pipeline mode.
Sure.
And,
yeah. Right. Yeah, that makes sense.
But it's kind of independent from the Python future package.
Yeah.
It's just a bash wrapper around how to send it to a cluster to calculate. That's all it does.
Yeah, and this is what like Dask would allow you to do.
Okay.
Basically, you program against like the Dask like task API, and then how those tasks get executed are up, like that's abstracted away from you, which is nice. Yeah.
Okay.
So we had a couple questions in Slack. What are the plans to convert the Fortran 77 code, now PyKelp, to a faster language, perhaps Rust or Julia, or maybe adding Dask? Now answered by the discussion with Will. Never mind on that one. Okay, different question. What resources would have been most useful to you when getting started, or even now? And would a How to Python and Heliophysics workshop potentially be of use?
In terms of resources, I would say actually someone who has a programming background and actually know what they're doing, as opposed of me trying to find the best Google answer to fix a problem and trying to figure out what's the best common practice between 4 common practices when you start going into one topic. Because for example, I went on the number route because of you do number to parallelize. And then I went into a whole world of pain of actually understanding what number does, and I still can't control it after years. It's magic. It is a black box. At least with the multi-processing thing, I know exactly what I allocate, how I allocate it, and what tasks are getting executed. And it's more linear and front end rather than whatever number does. And I can't convince number to give me the backend info to actually understand where it fails and what it does. But yeah, mostly I've been starting to use the PyHC resources that I found online more and more, and that's how I'm slowly going towards PyHC, just because this is a set of coherent standards.
Yeah,
and
definitely. Yeah, I mean, starting with our Slack in general and asking questions is good. I think there's a Python subchannel also on the US RSE Slack that might be a good resource. A lot of developers on there too. I can point you to that offline. Do we have any other questions?
Just to encourage you comment that you've qualified a lot, saying that you feel like you were just making things up as you went and you're just doing things, but you seem to be doing all the right things. So good work so far.
Mostly. Don't ask me about different personal opinions and so on. And hopefully I went into the right direction. I don't know.
Sounds good. Well, thanks again,
Thank you.
Alan. All right. We're officially in our lunch break. We'll be coming back at 1:30, so a little over an hour and 20 minutes from now. If you're in person, maybe we can figure out where we want to eat. Eties is open. It's just across the street. Of course, their online platform to order just went down, but we can still walk there. So thanks, and we'll see you in the afternoon. Sorry, say that. Yeah. I plan to. I feel like there's a better side.
But that's already, but I didn't know that that's the overhead.
It has like the array interface and the like data frame interface, and then which sort of look like NumPy and pandas. But then also just access of like basic that you can create like a client, and that client. You can create like dependencies, like tasks and depend on the tasks, and they know what order they need to execute it in. Yeah. So that's like the lower level. But that's
various levels of
you can use that on top of Slurm. So basically, you can build a DAS cluster that uses Slurm to send word to your.
Yeah, so like
then instead of relying on an external bash file to execute the Slurm, I just invoke it straight to the Python.
It's there's a package called DAS .q, and what it does is like dynamically generate Slurm submit scripts based on your tasks that you want to send to. It's kind of crazy. It's sort of a hack.
The general like flow of what you have some Python code that uses Dart, and if you run it in the same way that like using Dart array does, right? If you run it, it will parallelize it multiple queries based on the array by default. You can also say, oh, use processing instead of processing, or you can be like, okay, well, spin off this distributed cluster where you cross 100 nodes in clouds or you could be like, okay, use Dart job view.
If you want to go to e-test, we're going now. Here's your warning.
Absolutely anyone do anything Python. It's just create a different thing for running a task and all of the jobs just go, it just sends it off. It's beautiful.
So that's nice thing. You don't have to like you're from this just build create the cluster or someone else create better. Send it result back. That's all it matters. So you don't stop programming a bunch of different things.
So like if you're using Slurm, you've got a cloud
there's in this job queue, it's kind of gone a little stale, but I think it still works. They have like PS and Slurm and all the more like arcade. So it should just you should just be able to build one of those.
And like from Python side, like basic level, you can just there's like a multi-processing like API for Dart where you can do like run this function which you can put data.
Yeah, I know you set that up manually. Set up the start map.
But you can do that instead of using multi-processing, you can use Dart. It will use multi-processing when you're developing the thing, or you currently tell it that
in this architecture independent tool.
Yeah.
Yeah, we're all really it should run on any OS. It's really once you use it, you don't want to do control. Yeah, it's really I found it fairly to integrate things like your existing. If you're just having existing workflow, the one that you use things like just slot it into like whatever your existing workflow is. You don't have to change a lot. To get it.
Everything that I done was now I have a okay. Yeah, actually use the table that I figure out which function I should still keep working on non-vowel.
So from the perspective of using the only people whom I don't recommend is people who want to I wouldn't use number in like some right, like a big package like that we distributed to a lot of people because number is a complex runtime essentially, but it doesn't have that giving finding stuff out runtime on your user's machine. And like that makes it a lot harder. That makes it more like the user running the real education don't work properly. So I'd much rather see like some places next year more likely to work. Obviously more work for us. But it makes it like generally easier for the user.
That's what Nick was getting at during the positive presentation of why they dropped that. Because number is also slow to support. Sometimes it'll take a year to support like the next version of Python. So if,
I mean,
Well, no, but again, if you're like, if you're publishing a package that people might want to do.
they want to do it. Like if it's a year's at Python 3.13 or something, people would.
I would personally.
Which you also
I
just ran into this issue. I don't know, the company just go, I make an environment which is static and then I give it until it breaks itself.
Which is fair.
And then when it breaks, then I update everything, remove the recent things that I can, and then it's good enough. That's my experience. That's what I'm doing. Because I try to do it rolling and just install it without having things dependent, and then it doesn't work. It's too big of a. And I'm assuming now what I heard, the number was the start.
Yeah, I think it is. It's just a really complex tool, and what it does is really amazing, but as a result of what it does, it has the complexity.
The only way I can generate those databases is through the engine.
Yeah, no, it's amazing.
That's why function is so vital.
Yeah.
Yeah, so I can pull up the code to see exactly how to import it. So I imported from PyHC imported itself.
Oh, okay.
So I don't need, if I import PyHC, I have direct access to the CRT database.
Oh, okay. Oh, okay. So that's whatever they're doing on.
And let me see if it's PyHC or whatever PyHC import.
Okay.
But from what I know, I think Tom decided against it and he just has the environment variable and then as long as you update the local CRT database, it reads the things, just mimics the directory structure of the database.
I see.
Without giving. I tried importing the, what was it, PyHC. Hasn't been updated in more than a year and it doesn't work. The tutorials don't work. I couldn't make it work in any way that I could. And that's why I discovered this hack to find the thing.
Yeah,
It works.
I don't think you're experienced. That's what I would say.
The first tutorial thing, which is a pro.
Yeah.
If it's something sophisticated that's forgotten, that's one thing, but it's
like the first thing that it's often, I think, a frustrating experience. I don't think the docs are like this. No, itself, they're like they're separate. Yeah. People who can already deep dive into that plan.
Yeah, I believe so. I don't know how crowded it would be, since it's also one time for all the. Yeah, and different things. Yeah, I was gonna.
Patching up as well, so I think much stuff should work.
Yeah, so I still had some trouble with that, like downloading stuff.
Yeah,
I mean, file system is inside a browser container. It's really wackadoodle.
Yeah, making it all work. It would just be like so much effort.
In principle, it should work that way, but browsers are different.
Well, I mean, PyHC has a lot of that abstraction, but like even using those abstractions. those places are not very far away. So probably quicker than yeah, yeah. Use that part. For a long time, there was no like.
So do you come out to see your water?
Never really see. So where are you guys going? If, oh no, I'm. Okay.
What?
One of the Democrats said they must be said, one of the issues that Democrats deals in like high income base. They have college people. But if you appeal for the normal people, that's it coming up your coat.
Yes.
I want to implement tariffs and everything. Country emerge. Crack. My difficulty has to do with work, where if I put it to sleep and then resume, my keyboard stops working, so I'm probably back in the front. Just my keyboard. Don't know why. My old AMD computer problem. There was like this mechanical platform issue that we were using with people. But we used them. Yeah. A bunch of people found this with VR headsets with the problem. Son of a bit, what? Come again? I think VR, you got the motion lighthouse. Lighthouse. So apparently people found the VR, but VR letting full platform. Plugging USB ports on old AMD machines. This happens on my notebook. I like 80% of the USB ports, sometimes the device machine helps. Other people live without functional ad. Hey Julie, how do you live without functional ad?
Without what?
A functioning ad block.
Yeah, well, that's not my laptop.
So.
This is just the room's laptop. And
Good answer. The way. Well, I haven't got access to it, so. The way I do it is.
But isn't it so exciting to learn about bunch and flavor?
No.
Nuts or whatever it's called.
The way I use Firefox, get a good ad block, move on.
It's a dirty Chrome user.
Yeah, see, Chrome have ban-handed real ad block, so you have to give up Chrome and move to Firefox to get real ad block. The way I live without ad block is the websites that I visit. Pretty restricted.
I had to open incognito because I'm not on the market. I sent else's Google file.
Use a real browser with an ad block. Migrating out is not that hard. Really isn't.
I'm already trying to do.
On building CDF on Golden, yeah, have you tried that yet? No, that's why it's not. No, but like you haven't, like, I don't think done anything.
Try not be in my way.
Yeah, no, I was just curious.
But honestly, part of the reason for that is because
What the heck?
that's what easier than trying to do big fights. They don't let you. They won't let you, but
Okay, cool. You can go ahead and come up.
All right. We're going to kick the afternoon sessions off, starting with a fiasco update from Will Barnes.
Thank you. Okay. My name is Will. I think everyone in this room almost knows who I am. I'm a research scientist at American University and Goddard Space Flight Center. And I guess most of my kind of involvement in this community has been via SunPy, but I'm going to talk today about kind of a pseudo adjacent package that I've been working on for, I guess, a while now, since I was a graduate student, that's called Fiasco, which provides a Python interface to Chianti, which is an atomic database that's really useful for interpreting solar observations or kind of more broadly astrophysical observations. And I realized that I actually gave the first talk about this 6 years ago at this same meeting, almost to the day, in this exact same room. With a lot of these same people, I think, as well. But I haven't talked about it since then. So I figured I would give a quick, for one, reminder to people of what this thing is, since I don't talk about it that much, and then also just a quick update of what's happened in the past 6 years. Okay. Great. All right. So we get a lot of these really nice images of the sun. This is one from AIA. And we often interpret these like intensities in terms of typically temperatures and or densities. But of course, the question is, you look at the thing that the value that your instrument measures, especially in sort of a narrowband image like this. And the question is, okay, how do we know that this corresponds to 2 million degrees? And the reason is, of course, we know what spectral lines are observed in kind of the wavelength range that these instruments observe in. So this is the wavelength response is the dashed curve, which is basically like the envelope over which that image that I just showed is made from. And then these are all the kind of dominant spectral lines that pop up in this wavelength range. And you can see there's quite a few. And to make that image that I showed previously, you basically just integrate over this whole envelope or all this wavelength range weighted by this envelope by the dashed line. But of course, to understand, what goes in or what those values in those images correspond to in terms of like the underlying physics of the solar atmosphere, you have to know what mechanisms produce these spectral lines and at what intensities and density, or sorry, what temperatures and densities these things are produced at. And so the way that one of the ways in solar physics that we know about this is, well, in astrophysics more broadly, we have some knowledge of what processes produce the light that's actually being measured by these instruments. But that requires a lot of the detailed knowledge of the atomic physics that produces that emission. And so in solar physics, the kind of main resource we use to do this is something called the Chianti Atomic Database. So Chianti was a project that kind of grew out of efforts in the early 90s to make a lot of both atomic data and atomic codes publicly and freely available. So, there was kind of before that time period, everyone sort of had their own pet code and set of data that they would use to do these types of analyses. There's sort of a group that came together. There was a collaboration between George Mason, NRL, the University of Cambridge, and some various institutions in Italy as well, to sort of make these tools, to standardize on these tools and make them freely available. And so this has been going on for quite some time. There's a first release in 1996. There will be a version 11 release later this year. And so this has kind of been a longstanding and ongoing effort with a lot of active members across the entire world. So the database itself is a collection of just plain text files in various formats. Most of them are sort of like fixed width format. If people are familiar with that. The total size of the database is like 1.5 gigs. So it's not massive. It's not big data, but it is often, the size makes it often difficult to deal with. The software traditionally has been written in IDL, and it's usually just used to parse the database and to compute sort of different derived quantities, usually for computing these spectral lines that I'm showing here. And there's also some GUI capabilities for that are really useful when you're doing like spectral fitting, for example, or trying to understand what lines appear in the wavelength range that I care about for these different conditions. This is a fairly old software project, and as you might suspect, it lacks kind of a lot of the sort of things we expect out of modern software development, like automated tests. It is freely available, and it always has been freely available, but I would not say that it's openly developed. So the team that develops it's not that they're averse to contributions, but it's sort of a closed development process. And there's also not a lot of backwards compatibility. So the way the database and the code are released, they're released together, and that version of the code works with that version of the database. And once you, it's very hard to sort of roll back to previous versions to say, what will my result look like if I use like Chianti version 8 versus version 9, for example? That's not so trivial. There actually has been a Python tool that's been developed since around 2006. So this has been around a long time, especially in the Python world. It's called Chianti Py, which people might be familiar with. And it's one that I worked on for a bit when I was a graduate student. But there were some, I guess, differences in the way Chianti Py is developed versus, I think, a lot of the ways that we in this community expect to develop software, and as well as some of the more specifically on the SunPy side, adoption of things like AstroPy units, modern testing practices, et cetera. And so what sort of ended up happening was that I, as a graduate student around 2017, started developing this thing that I called Fiasco. The reason it's called Fiasco is because that is the name for the style of bottle used to serve a Chianti wine. And also, I think it's just a funny name. And so I started this effort around 2017, just on my own, basically. My PhD advisor was connected to the Chianti project, so it wasn't totally a coincidence. But so this was started, when I was late in my grad student career. I didn't do the first release of this formal release onto PyPI until January of 2023. So this has been quite an effort. I just did a version 0.3 release in September of this year. Again, uses all the kind of usual stuff that we expect these days. It's developed openly on GitHub. It uses GitHub Actions and a lot of the nice CI templates that we developed on the SunPy side to do all the testing and releases. It's hosted on Read the Docs. I would say one of the biggest advantages, so in Chianti, there's constant confusion, especially in the IDL tools, of what units you need to put into something and what units you're getting out. And because there are different, well, I guess one of the big ones is on the EUV side in solar physics, people love to use angstroms when they talk about sort of wavelength or spectra. Once you go up to even slightly higher energies into like the X-ray community, they use keV. Chianti, the IDL tools support both, but it's constantly confusing of what are the units you're getting out of the package, and it's usually denoted by a keyword, and there's all this logic to deal with that, blah, blah, blah. So one of the advantages, I think, of Fiasco is it uses AstroPy units everywhere, and it just makes all this kind of stuff way, way easier. I also use Plasma Pi, some parts of Plasma Pi that Nick mentioned earlier in his talk, and particularly the particles class, for dealing with how you parse like the designation of a particular ion or element, and I'll show that in a second. The other big feature, I would say, is that Fiasco, I mentioned that the database is just a collection of like thousands of plain text files. What Fiasco does is it parses every single one of those files into a single HDF5 file, which means that you can pull out only the part of the database that you need. you don't have to read in the whole text file or a whole set of text files. Some of these can be really large, hundreds of megabytes. Reading in hundreds of megabytes of plain text every time, it turns out, is kind of slow. Okay, so what does the code actually look like? Kind of the building block of Fiasco is this ion object, and basically everything else is kind of built up around these ion objects. So the database itself is sort of organized into a bunch of subdirectories, and there's basically a directory for every ion in the database, and there's a bunch of data attached to that ion. So it's kind of a natural way to organize the code as well. So you can create one of these ions by just putting in some sort of designation for the ion. You can do this various ways, but for example, this is iron 14, which is an iron ion with 13 electrons removed. So you might see this designated as like iron 13 plus also. You give it a temperature range, and you can access different sort of bits of metadata. So this is just the repr that it gives you back if you just print the object. You can see, okay, it tells you what element it belongs to, what's the charge state, how many levels are available in the database, and how many atomic transitions there are associated with that particular ion. And then also things about like what, I ran this on my computer, so it's looking for a particular file. And so what happens is that it builds the database once, this HDF5 database once from all the ASCII text files, and then it just reuses that same thing again. So you build the database once, it takes a little bit, but you don't need to go through that process every time. You can also access kind of various bits of metadata. Of course, this thing is right on top of where I want. Like the ion name in different formats. You can access the ionization potential, and here I'm just showing that the ionization potential is actually expressed in ergs, but you can convert it to EV easily because it's just an astropy quantity with a unit, or the abundance, the abundance relative to hydrogen. I learned a lot building this package actually about the kind of crazy things you can do with Python objects, like that you can allow them to like be indexed in the same way you would index arrays, or you can define arithmetic operations between objects, which is kind of a fun exercise. So the one kind of cool thing that you can do is that you can why is this? You can index an object like you would a list, and you get back the different energy levels associated with that ion, which is just a nice way to kind of be able to inspect each of these objects. Okay, so one of the main advantages of this database is that given the data that's in the database, you can compute kind of derived quantities from those data. So one of the big ones is if you want to compute what is the ionization balance across an element, you want to know the ionization rates and recombination rates as a function of temperature. And so this is done easily by just these properties that I'm highlighting here, and that you'll see a plot of in just a second. But because it already knows about the temperature, it already has access to all the bits of the Chianti atomic database that it needs to do this combination. It's just a matter of calling these properties. And this is just showing a plot of the ionization rate in blue and the recombination rate in orange. And then the dashed and dotted lines are sort of the components of these total rates. And so it makes it easy to sort of inspect, for example, you might want to know at what temperatures is the direct ionization rate dominant over the excitation autoionization rate, or the different recombination rates as well. Okay. So in addition to these like building blocks, you can also combine these ion objects in kind of interesting ways. So another kind of component of the package is something called an element. So instead of just designating a single ion, you can say, I want to build an object that represents the element of iron, give it a temperature range. It kind of works similarly to how the ion object does, but what this element object does is it holds all of the then ion objects associated with iron. So, iron 1 through iron 27 representing, neutral iron versus fully ionized iron. And then it holds all that same information that you would for a single ion, but just all bundled together. But then similarly, you can access like the individual ion components by just indexing the element object like you would a list, similar to how you index the ion object to get at the energy levels too. And you can see this just prints the repr for that individual ion object. So the reason that you might want to hold all these together, there are particular processes that operate between different ionization states of a given element. One of these, which I just sort of alluded to, is the the ionization balance in equilibrium. So basically, you're just saying what is the fraction of any given ion that's present as a function of temperature for that element. And that depends on the balance between the ionization and recombination rates of adjacent ions. So just an equation a system of equations that you solve, but you need to know about all the different ions in a given element, not just one on its own. And so you can make a plot like this by just calling this equilibrium ionization, and it knows how to, because it knows all of its ionization states, it can use those derived quantities that I showed previously to build up the system of equations and solve this. And this is a very common quantity that we use, especially if you're like a spectroscopist or even doing sort of imaging analysis that you would want to know. Okay. More generally, you can create just collections of ions that don't necessarily share, like aren't in the same element. For example, if you want to build up a spectra that contains many components, for a given wavelength range, there might be many different ions from many different elements within a short range. Or if you're trying to compute what the radiative losses are as a function of temperature for a plasma, this is a really useful thing to do. So you can actually directly add ion objects together, and that creates a collection of them. And again, like I alluded to earlier, this is just by overriding how arithmetic works between these objects, which it turns out is really easy to do in Python, is actually really fun. Okay, so now you have a collection of these two things, and then in the same way that you could do before, you can actually index out each one of these. And so this is what I'm plotting the radiative losses for just the first component of the collection, which is just the iron 18 ion, but then I'm adding in this oxygen 6, which is a much cooler ion, which is why you get radiative losses at these lower temperatures. So the orange curve is the total collection radiative losses, the blue is just the iron 18. Okay, so this is my last slide. I just wanted to kind of summarize by saying, what has changed since I gave this talk 6 years ago as a graduate student? Not as much as I would have liked, to be honest. But so now the package compared to then, it was just available through GitHub. You had to install it from source. Now it's available on PyPI. I think I've gone through 4 or 5 releases. There are a couple new features, including the ability to do continuum calculations that match quite well with what's done in IDL. There's support for a couple new data formats that have been in the subsequent Chianti releases. There's been a lot of systematic comparisons between what's in the IDL code to make sure that for every change, we're consistent with the existing tooling, so people aren't surprised when they switch from IDL to Python. There's been a lot of work on the documentation. And in particular, I've managed to attract a few new contributors, which has helped the project grow, and which has encouraged me to continue to work on this. This is now sort of formally associated with the Chianti team as well, and I am as well, mostly because of this project. And perhaps most importantly, I now have dedicated funding to work on this through the internal scientist funding model at Goddard with Peter Young, who's one of the kind of founding members of the Chianti team. So in the future, hopefully support for newer versions of the database. So the Chianti database is updated at a semi-regular cadence, probably every 2-ish years, as new both approaches to doing these derived quantities from the atomic data become available, but also as new atomic data become available, need to be folded in. But it means that I have to keep pace with what's done on the IDL side, which is always, or that that Fiasco as a project has to keep pace. What I'd also like to do is have better integration with PlasmaPy. So during Nick's talk this morning, Nick pointed out that there's this PlasmaPy particles part of their package. I'm actually not really using very much of that, but it would be great to sort of, there's a lot of overlapping functionality there that we probably should be able to kind of subclass what they've done on the PlasmaPy side and just have kind of specific attributes on top of that for the Chianti database. So that's something that we've talked about for a long time, but just hasn't come to fruition yet. Yeah, so that's all I have. Thanks. No. No, so the Fiasco code is licensed. The database is not. And I don't know why that is. Yep. Yes, Stuart.
Why you couldn't copy the database version, convert it to HDF5 and stick it onto Node?
So the question was, is there any reason that we couldn't just convert every version of the database to HDF5 and stick it on Zenodo? No, there's no reason that we couldn't do that. Yeah, no. Yeah, and that creates kind of, it also means that there's sort of this like yet another version of the database, right? And it means, and this is something that I've kind of thought about for a while. There's not really any good reason not to do that. I will say building the HDF5 version of the database is pretty straightforward, and it actually doesn't take that long. But yeah, we certainly could, and I think people have kind of toyed with that for a while because dealing with thousands of plain text files is kind of a pain. Thanks.
All right. We have Joe. It should be. Yeah, do you want to just share on Zoom from your laptop? Okay. Yeah, it looks good to me.
Thanks. All right, so I'm going to be talking about the EM toolkit code for doing DEMs that I've been working on the past few years. This is a NASA-funded project, and the basic pieces are now complete, and our current funding round is finished. So this is going to be kind of a wrap up for the current state, but I'm not necessarily going to stop working on it or anything like that. So I'll start off by talking about what is a DEM. So here I've plotted AIA 193, and you may have heard of this channel, and people have mentioned that it shows a temperature of about 1.6 million Kelvin. There's another one, AIA 335. It's a little hotter at about 2.5 million Kelvin. Well, what does that temperature actually mean? These observations show not like the amount of material, but the distribution of density squared as a function of temperature integrated over the line of sight. This is a limitation that is given by the way spectral lines work, to exactly those temperature response functions that Will was talking about in the previous talk. And that's just, they respond to different temperatures, but they respond to the density squared at those temperatures rather than the density. And this quantity is called the differential emission measure. And they encapsulate all that these observations, your typical EUV observations, although there are exceptions, can tell us about the temperature in the coronal plasma column that's being observed. So to kind of summarize, each plasma column has one of these one of these distributions of temperature squared, the middle plot in this figure. And it might have some temperature at a little over 1 million Kelvin. That's represented by 60 here. I should apologize about these units perhaps. And less at others, and then more further up. And each pixel on the sun has one of these things. Those are then integrated against these temperature response functions, which are the curves that come out of taking Chianti and Fiasco, for instance, and integrating them against the wavelength response functions of the telescope in turn. And so that gives you a number at each pixel, that integral does. And you take all of those pixels together, and that is what produces your EUV images. So that whole process of per pixel integration results in the images that you have. The DEM inversion game is, suppose we have a small number of those images. How do we turn around and turn them back into the distribution of density squared as a function of temperature that's present on the sun? And this just sort of schematically shows that process. You have a coronal source that has one of these DEM functions at each temperature. At each pixel, it's integrated against the temperature response functions. That gives us a set of images. That's our starting point, together with what we think the response functions are based on the work that goes into Chianti. And then we try to turn them into these DEMs that give us an estimate of a pure temperature image on the sun. And there are a variety of algorithms that do this. I've written a couple of them. One of the issues is that this inversion process is ill-posed. The algorithms have to make assumptions about the structure that's being observed. And what you get out depends on which assumptions you make. The existing algorithms are mostly in IDL. They have different formats for inputs and outputs. So we propose to create kind of port a few of these algorithms to Python, and make a standardized interface for how they talk with the data and what the output looks like, and also write some visualization tools. And that got funded a few years ago, and we've been working on it. This is sort of how our data structure looks like, and the paradigm that we went with is we don't try to like modify the algorithms themselves. Instead, we write wrappers around them that puts things in the standard interface, and the EM Toolkit core is this sort of container that can hold data and DEMs corresponding to that data. And it's more of a, it's built on IndyCube, but it's really more of a string bag than like some rigorous like organization thing. And we also have algorithms that show DEM products and a dashboard. And I'll show that here. So this is that dashboard. And it does some fun stuff, like you can mouse over the image and it will show you that DEM function at any given point in the image. There's a couple of different algorithms, DEMs for algorithms represented here, and you can switch between them and see what the differences are. This image here is actually created from the DEM using these like synthetic channels here. And you can actually change the properties of those. Let's see. Like I made the temperature that the red channel responds to lower. So you can get a different result here. You can also, so this cursor that it shows the DEM at the cursor location. You can also click and step through, basically click on different points in the image, and it shows the DEM along this line in this 2D plot here. And there are a few other features in here as well. But this is kind of intended to be like a starting point to let people see what's in the DEM. Because it's a 3D cube, it makes it harder to like interact with. So I think this is sort of like a baseline for helping people to do that. Moving back to the slide. Okay, so the current status is that the basic structure is present, I think. We translated the two main algorithms we set out to do, Mark Chung's sparse EM algorithm and my simple reg DEM algorithm we didn't try to do anything special when we translated them. We just tried to move them verbatim from IDL and to Python as much as possible, and then we wrote wrappers for them that spits out the stuff in the standard format. We wrote the visualization. We also wrote instrument wrappers for AIA and XRT. We made the visualization dashboard that we showed you. There is a work in progress, somewhat work in progress documentation on the GitHub site for the project. And there's also a new multi-instrument algorithm that I worked on that solves the DEM in X, Y, and temperature. And that allows it to incorporate multiple instruments in a resolution agnostic fashion. And also at the same time, it can correct for, it can take into account the differing spatial PSFs of the instrument, a variety of other interesting things. And we also did a basic downsampling multi-instrument algorithm that can work with AIA and XRT, for instance. So the current funding round is about finished. We may look for more. Like I said, I'm going to continue to actively use it for various projects. A couple of things would be good to add, like error estimation, being able to export subplots of the dashboard that I showed you, able to showing time series plots on the dashboard. I'm currently kind of wondering what the right thing to do going forward is, if sporadic long-term NASA grants is really a viable option. Can I transition it to just being a community-run thing without direct funding and input? Is this the package for DEMs that we want going forward? Those kind of questions. I do think that the multi-instrument stuff that I added to it is pretty interesting and exciting, and I'd like to see that paradigm propagated forward. So that's it.
Do we have a question in the room for Joe? Let's see if we have any online. Not right now. All right. Well, thanks, Joe.
Thank you.
You're up next if you'd like. Yeah, if you're sharing.
Thank you.
And again, if you have questions later, we have threads for each of the presentations in general on the PyHC Slack. Yeah, so far I'm just seeing you on Zoom.
Zoom says I'm sharing.
Definitely sharing.
Yeah, let me see. Does that work? No. Sorry, technical difficulties. My computer has decided to disconnect from Wi-Fi.
That explains why I'm not sharing. Oh, it's on ED room instead of wireless.
Yeah, UCB wireless just doesn't work for me. It kicks me off every 10 minutes. And apparently Azure Roam has decided to do the same thing.
Well, they're on Drive.
The slides are on Drive, but my demo is not. All right, disconnected and reconnected.
Hold, please.
Ah, there we go. And does it work if I put it in presentation mode? It does. All right. Hi, I'm Gavin Medley. This is going to be really quick. So I develop an open source package called Space Packet Parser. And I previously presented these slides in this demo at the Science Data Systems Workshop meeting in October. So apologies if you've seen this already. Also, big thanks to Greg Lucas, who has done a lot of development on this, and the whole IMAP team who's been helping me test it. So this library is basically a CCSDS telemetry decoder. And the reason I'm presenting it here in PyHC is because everyone here uses CCSDS packets for downlinking data across pretty much all the NASA divisions. Pretty much whatever spacecraft you're using, you're getting CCSDS packets as the telemetry, and that's sort of the L0 data product. Comes in a few different flavors, but essentially this is a telemetry decoder for those packets. We use XTCE as the configuration basis. XTCE stands for XML Telemetry and Command Exchange Format, and the XML is a pain point, but it's pretty workable, and it's about the best configuration format we've found so far. CSVs are nice to look at, but not easily parsed and not very consistent. So we went with XTCE. This allows you to configure the parser external to the code base. So you can write all your decoding code, all your algorithms, and then just feed it a configuration file. And that configuration file can change as the packets get changed during instrument development, which makes this really useful for making quick look tools. We can handle pretty complex packets. That includes polymorphic packets, multiple variable fields, variable length fields, and all kinds of things like calibrators built into the packet definitions, enum lookups, things like that. It's already being used on multiple large missions, and we develop it here at LASP. So IMAP is using it, Libra is using it both for the integration and test data center and the science data center algorithm development. MMS is using it in a limited fashion, and Clario Pathfinder is using it, as in addition to a few CubeSats here and there. We have a roadmap for some new features and easier packet decoding. So that's kind of an abstraction layer on top of the low-level API that we already have. And that's, I'll talk about that a little bit more later. Come on. So we just released version 5. If you've ever used this, it contains some breaking API changes. I'm going to skip over this because you can come talk to me or put up a GitHub issue if you have any problems here. We fixed some major bugs. So we now have full support for string data encodings. Not that very many people actually use string data encodings, but we support, oh gosh, my Zoom is now reconnecting. This could be a problem. It's still up there, so I'm gonna keep going. Oh, there it goes. Sorry, Julie. All right. So we now have full support for string data encodings. We have a better abstraction for the CCSDS packet class that we actually return. It's a little more intuitive. We added some support for some additional encodings for floats like MIL 1750A and some time data types that was contributed by Caden Gobat at Sweary. So thanks, Caden. Here's our roadmap. So we're looking at finding a way to directly return an X-array data set object from the parser, because most people, I think, are using NumPy or X-array to actually work with the packet data, the telemetry data. So we're working on that abstraction. We're going to build some CLI tools for directly inspecting packet files, especially headers. That's really useful for ops teams, maybe not so much for you guys. And we're working on a CSV to XTCE conversion tool because I know that a lot of people like to work with packet definitions in CSV formats. The trick there is figuring out what CSV format we want to support. And we're also working, based on some feedback at the last meeting that I presented this at, some support for continuation packets. All right, sounds good, John. Here's some resource links. These slides are in the Google Drive, so if you want to go find these resources, you're welcome to. And then I have a quick demo, which I have about 5 minutes for. All right, so we're looking at DeepNote, and this is essentially a cloud-based hosted Jupyter notebook. I don't want to deal with managing it for the purposes of a demo, so just using their platform here. I've set this notebook up to pip install the library, and I also have some demonstration data here over in the files on the left, so it has access to all of that data. So I'll just run through this really quickly. We kind of set up this data directory. You can see kind of the, yeah, this isn't really important. We're just setting up the data directories here. Basic parsing here, this is kind of the core of Space Packet Parser, at least the low-level API that we're currently exposing. Again, we're working on some abstractions here to make this a little bit easier. But essentially, you open your packet file, you create your packet definition. So you create your packet definition first up at the top. That's XDC packet definition, and then you pass it the XDC document file. So when it does that, it actually parses all of the XML and figures out the structure of your packets in a way where it can actually dynamically solve the structure of a packet based on any restriction criteria you put in there. That's how we get the polymorphic packet capabilities. Then for each packet file you have, you pass it to the packet generator here. That's a method on the definition itself. And here we go, lost connection again. Sorry about that. I hate our Wi-Fi so much. Is that recorded? Oh, great, perfect. And we're back. Okay, so you pass it to this packet generator method, and we're using a generator pattern here just to save memory. It allows you to inspect individual packets without having to parse the entire thing all at once. But of course, you can just call list of the generator if you want all of them, which is pretty much what we're doing here. That's exactly what we're doing here on line 9. We're timing everything to get an idea of how fast things are going. It looks like we're getting about 53 kilobits per second. I have to say this, it depends what platform you're running this on. On my local machine, we get about 16 megabits per second. So there's something going on here with the resources available to this Jupyter notebook. It's a little slower, but still a reasonable packet rate there. And we make this full list of 86,000 packets for I think this is a 24-hour day of JPSS-1 geolocation packets. Okay, so this is just kind of an overview of the packet definition object. By the way, I'm going through this fast, but there's a link to this notebook in my slides. So if you want to go play, at least see this, I don't think you can run it, but you can see it from the slides. So this gives you an idea of kind of the representation that we give here. If you want to print out the header here, or these are all the named parameters. So it's starting with the CCSDS header. And it gives you the type. So we're telling you that the version in the header is an integer parameter type, which makes sense. And you can kind of scroll all the way through everything here. There's even long descriptions, short descriptions. This is all based on what is in the packet definition itself. Then if you print a specific parameter type, you can say it's a float parameter type. This is its name. You can also print the short description, the units, if those are specified, optional. And you can print the actual encoding that the data was parsed using, and that's IEEE 754 as a float for this particular data item, which is the ephemeris velocity, ADGPS-vel-x. So if you actually want to work with individual packets, you can print the packet, the full packet, the raw binary data that was parsed, and that's kind of just a small chunk of the original file that went in. All the full parsed values for that, including any calibrations or derivations that were done to those raw parsed values. You can also get the raw, the actual raw encoded value if you want. And there's an example of what comes out here. This is a quaternion in this case for the attitude of the JPSS-1 spacecraft at that time instance. Same thing for parameters. You can get all kinds of information. The raw value, here's an example of that. In this case, there's no derivation, so the raw value matches the kind of more derived value that you get by default. If you're using calibrators or enum lookups, the derived value will be the derived value, whether that's an enum lookup string or some sort of calibrated form of the raw value. And then with working with the data, I'm just giving an example to parse this into Xarray. And this is essentially like, this is basically taking from prototype code that we are now going to incorporate into the repo for directly returning an Xarray object from the parser. We do some massaging to move the data around a bit. But ultimately, you can see we're making an Xarray data set where all the data vars are the param names and the param values. And the coordinates are the epoch that the data was taken at. So that's from the secondary header. And we write it to a netcdf file. So you can see we're writing it to this one, 2021-0409 JPSS geolocation.nc. And then we're just reading it back out to make sure that we can actually read that file. And so this is kind of an example of what you will get out in the next iteration of Space Packet Parser. So you give it a definition and a telemetry file or multiple telemetry files. And as long as they're all the same app ID and packet structure, you get a giant Xarray object that you can then use in your data processing. And we lost Zoom again. Okay, I'm going to call it there. So again, those slides are all, the links to all of those resources that I showed are in my slides. Those are on the Google Drive. We have a GitHub repo. We have Zenodo if you want a DOI for the code. That's all up there for every version. We have a formal release process. We're on PyPy. So if you have any questions, there's lots of ways to contact us through those resources.
All right. Do we have a question in the room for Gavin?
Yeah.
Hey, Sean, where'd that extra mic go? Oh,
So I remember the last presentation you gave, roughly last month, the one that you mentioned. And in that Q&A, there was some questions about, hey, I was trying to wave at you earlier, some question about collaborating with Daniel De Silva. How has that progressed, if anything?
So Daniel's library and my library kind of start from different conceptualizations. I think that Daniel has a desire to add XDCE support to CCSDS-Pi, and I think that's a great idea. We're also obviously adding CSV support for some format of CSV files to our library. I have offered to, I mean, obviously our library is public, so he's totally free to use it as a backend to CCSDS-Pi, and that's kind of what I suggested. The last time we talked was in June, and he was working on his PhD thesis. So I think that went well, and I think he's now back to working on CCSDS-Pi. So I've sort of left the door open and offered them any support that they need if they want to integrate Space Packet Parser as a backend. But at this point, we're not trying to like merge the libraries together. They have slightly different use cases. His is very much for efficient parsing of packets, and mine is very flexible. Space Packet Parser can do, it's a little bit slower in some ways because it can't read data. It can't parallelize the reading of telemetry data because it supports things like variable length packets, polymorphic packets, and that's fundamentally incompatible with the NumPy-based approach where you just read where every telemetry item is in a fixed length packet and read them all at once. So those two modes are pretty conceptually different, but they both have great use cases in the community, and I think we should keep them both. Does that help answer your question? I think the last time we talked was over a GitHub comment string in July or August. Okay, will do.
I think that answers your question that you'd had too. I'm just curious, all the missions that it's used on are Laspian missions. Is there a case to push it further outside of Laspian?
We are trying to improve so I've been working with, I've been talking with some folks at Sweary. I think people on the Punch project in particular. I think they're far enough along in development that I'm not sure they're going to use it for production, but they are certainly interested. So we have an email chain going back and forth. Yeah.
Awesome.
And we did apply for funding through Roses, but we did not get it this year, despite having excellent marks on every part of the proposal.
They must have just had a lot of submissions.
I think they just ran out of money.
Yeah. keep trying. It'll come back.
One is which Rose's element were you applying to? Okay, then I'm not even going to bother. They ran out by their own money. No, I mean, we're almost certainly going to be using this on Helios Swarm because I see no reason to use my crappy code anymore. So
Great to hear.
Cool. Any final questions for Gavin? All right. Thank you. Hey, Sasha, you online?
Yes, I hope you can hear me. and
Yes, we
maybe,
can.
maybe even see me. All right. Let me know when the presentation appears.
We can see him.
All right, so I guess I can start. Hello, everyone. I would like to be in person, but unfortunately not today. And yes, for those who don't know me, I'm Alexander or Sasha Drozdov. And I would like to give an update on the radiation balance analysis and modeling library, or RBM LEAP. This will be a project update following from what I presented last meeting. And this is the result of NASA HTM grant. So I'm pretty much a solo developer with a lot of ideas and help from community and the folks here. So what is this library? It's the lightweight Python library that's supposed to help for modeling of the radiation belts. And the vision is to provide an open framework for the contributing to this library. And as of today, as of right now, so as a progress update, I have a GitHub page. I actually created this radiation belts organization that I hope will be a home for other projects, and a few projects were already there. I do have to set up read the docs, and I do have set up. I did have set up the Python packages repository for that. So the library aims to, it's pretty much a very simple concept. The library aims to contain a calculation for system properties such as adiabatic invariance, drift velocity, space-phase density, etc., and empirical models. And the idea here for both of these options are just take the equations that we usually use. If we have an equation in the published paper, I quite often retype it from the publication, and that's inevitably lead to typos and mistakes. And if we just have it coded once and easy to install and use it, then it eliminates the errors. Well, I've done this retyping more than I should. So hopefully that will be changing now. And finally, I've been doing this modeling support for the radiation belts modeling. I have a lot of experience in modeling, and I would like to share it with the community, essentially. I did it a lot in MATLAB, and this code is scattered and pretty much inaccessible and not documented. So now I'm finally, with the help of this grant, thankfully, I will try to make it better and accessible and actually useful for people who do radiation belts modeling. So the current status of the library, the conf or conversion package was fully implemented. It provides the conversion between adiabatic invariance. And actually the first version, going a little bit ahead, but since we talked about this today, the first version was already used in Komodo, which originally I didn't think of, but then since I was in parallel developing this library, I thought that's actually an excellent synergy, and here we go, it's already found to be useful. As for the model packages, the plasma pause models were implemented, magnetopause model for Shu et al., a dipole field model were implemented, and there is a lot of other models that I included just before this presentation. They are empty kind of placeholders right now, but that's essentially reflect what I wrote in the proposal. So the content of the models, at least it's already there. For future reference, and plus it makes it easier just to develop it further and feel the functionality. I'm following the test-driven approach, so there's a lot of tests are written, and I will talk a little bit more about that later. I did manage to create an automatic generation of the Sphinx documentation. So every time there is a pull request to main branch and to development branch, corresponding version is created. I did spend a lot of time writing a contributor guide, and I will be updating it. So because I'm still figuring out what's the best way to organize the library in a useful and possible way. As I said, the first version of the package is published and has been used in Komodo. And as for the other folks, it's been demonstrated and used by GFZ, but this is not very surprising because I'm closely working with this group and they seem to be very happy. So documentation, again, I had, it was inspired by Plasma Pi style, and I'm really grateful for that. And basically, the idea is the user can go look at the documentation, find the equation that's they're looking for, and look at familiar documentation. If needed, there is a reference to all the papers. This is pretty much the format that I'll try to follow. And then straight up using the model as it is. And hopefully that will just mitigate, again, the same. I will repeat it again because it's the main philosophy that I'm following. If we have an equation, we can code it and use it once. So those empty functions were, again, included. I put a little admonition flag, and again, this is all available online in the dev folder right now. One interesting thing that I would like to share with the community is I wanted to synchronize the README MD file with the Sphinx generation, what I see on online. And I end up in an interesting problem that I was trying to solve, and I went to the rabbit hole and probably spent way more time for that. You can see this. There is a little bit of this admonition that is generated by the Sphinx, and if we go to the GitHub page, we also can see it generated correctly. But it's actually was not that easy problem to solve because on the GitHub, it expected this format for this admonition. On Sphinx, well, particularly in Mist extension, it requires a completely different type. This is Markdown text, and this is not even a Markdown text. This is a GitHub version of Markdown text with GitHub alerts. And that one is restructured text, of course. And following just I wanted to make sure that my documentation is isolated. It's in a doc folder, and only RST files are there. So following the actual guide from Mist, this is how you include the AMD file, the Markdown files, and this is how they rendered within the Markdown just language. So in order to make this conversion, I cannot just replace the text. I had to figure out how to write a plugin for Sphinx documentation. That would be the first one. There is even a GitHub discussion about that this plugin is needed, and I'm planning to actually send them my solution and maybe contribute and maybe even create additional plugin for Mist package itself. But what I had to do, I had to go through the entire document and find the corresponding node and change this node type to admonition. Then it renders correctly, and then I see it on both on the MD on the GitHub and on my documentation at the same time. So kind of proud of this, but went on a rabbit hole. So for testing, I have, you can see there's a lot of testing running right now, and some of them are very basic, but I want to share this experience with you. And actually, I wanted to say that I would like to hear more stories like that, because it's what I'm about to say, it's maybe trivial, but I personally learned quite a lot from these meetings, and I hope to hear how the code can be improved and how my coding style can be improved. I'm not a full stack developer, I'm a scientist after all. So here what I did, I introduced a very simple test. As soon as the function is included in my framework or in my library, I include just a basic test, and I actually even creating a test helper class. And when I create my test for the entire package, I inherit this test class, and then I can use it across multiple packages. And that actually caught some errors, and I was able to fix it right away, because this is the way how the function is supposed to be imported, and the way how I design it. So each function has its own package, but similar to what we do in PySpeedas, we just, or in PyTplot, as a matter of fact, in the ini.py, we import the function itself. So you don't have to import it twice, like ba2000.ba2000. So just RBM leap models DLA ba2000. That would be the function, but it is live in the ba2000.py. So just a little quick tip that was interesting for me. So as for the nearest plans, I would like to finish, of course, implementation of the models. I did have actually already preliminary discuss or to include additional models that I did not originally propose. That would be the pitch-angle distribution from Smirnov et al. But I'm actually co-author in this paper, so it's not a big surprise. And also isotropic boundary that is not even published yet. So, but I already got preliminary agreement that Colin Wilkins will be willing to look into that. I want to include the testing as the automatic GitHub actions, have not included yet. But then there are some challenges that I'm facing, and one of them is community engagement. It's, I guess, the part of it, besides PyHC meeting, I didn't have any other platforms yet to present these results. I'm planning to show it later today after AGU, and hopefully get a little more engagement from the community and see who can use this library. I originally thought that I would like to do automatic package deployment upon releases, but I don't know if it's easy or it's even possible, so I will have to look into that. And one of the questions that I have, and I really like to hear a community feedback, is how to actually include some data to functions. So, for example, here's this pitch-angle distribution model from Smirnov et al., and it uses this PIJK coefficients. And most of the functions, they don't require to use a lot of data. It's basically a tabular, some sort of tabular representation that can be even published in the paper. But then I have multiple ways how can I address it. So I just write down 4 of them. One is to include the data within the repository itself, similar to what PRBM library does in the form of CVS or ASCII files, so it can be easily changed and the Git will recognize it. Or maybe include the binary data. The benefits of include binary data is that we don't lose the precision if the data is somehow available through binary representation. But then I don't know what to use. Maybe GitHub large storage, but I'm not sure this is the right way to do. Another way is to download it on demand, similar to what PySpeedas does every time we request the data. But again, this is not the data. It's literally just a table of coefficients that sometimes has to be used. But since the library has to be lightweight, I'm afraid that at some point, if I start to include the data, there will be a model that's require a lot of data and the package will not be light anymore. And like some sort of Arduino approach is when I can include the data within the source code itself. But I've used it before. I don't know if this is the best way to go forward. So as a point right here at the bottom, I really would like to hear advice from the community, and I would really appreciate. And this slide I showed last time, it's my last slide. I would welcome the contribution. Please send an issue, and if anything, you can write me an email. That will be all. Ready to have any questions?
I know I saw 1 or 2 in Slack. Do we have anyone else in the room with a question? It would appear now. I see nothing in the Zoom, so I will go ahead. Nick just has a comment. Great work on the documentation. There's this saying in Plasma Pi that Sphinx rabbit holes often have dragons in them.
Yeah. Thanks, Nick.
Thanks for that. And okay, I see an actual question here. What file sizes are you dealing with?
So unknown for now. So for now, those are really small files. Again, it's just a tabular data that should be used in the model. Like for this Pichangular distribution model that I'm looking at, it's probably a few kilobytes. Also, one of the model that's I was not originally planned to include, but I think I can include, is the one that's we developed for the scaling of diffusion coefficients. It also has a few kilobytes, and most of the time, I think that would be it. That would be a very small, like tabular data that again can be even included directly into the source code, which is good for the Git, but I don't know if it's good for the representation of the data modeling. So it's still something I'm trying to understand what will be the good way to deal with that, or maybe have some guided restrictions. And if there is any heavy model, then maybe there has to be a correct documentation how to download it and use it. So that's an open question for me. Yeah, so that's like, I see the Slack now. So the question is like, if I can put them on Zenodo and download them there. And again, that will be downloading on demand. The only problem is if I don't have internet connection or anything like that, then you have to do it sort of in advance. And for large data set, maybe it's a good idea, but for small, would be not. So I would be happy to have this discussion, like maybe in a separate thread and in the issue. If anyone who is interested to do that, please join. And the reason why like want to spend some time in the discussion is because we had the conversation about SpacePy, and the SpacePy right now is actually like originally it was a larger package. Now it's comparable size with what I have, and maybe in the future when this grant will be finished, I'm thinking maybe this RBM library could be integrated to the SpacePy to reduce the overhead. But this is another thing that I'd like to hear as a committee, or maybe just use it as it is and use it as dependency.
Awesome. Thanks, Sasha. I think
Thanks.
you have one more question coming your way in Slack. So just keep an
Yeah.
eye.
Thanks.
All right, one second while we get Sean's presentation up here.
I actually have my microphone here.
Oh, yeah.
Sweet, thank you. I'm gonna give myself just 1 second to check to see how the video here made it, because I have one quick video slide. No. So here, I'm actually going to need to get to the Google Slides version of my slides, but I have that. What's a quick way I can get that? One second, I have to, I think, do a Zoom chat to Slack myself the link here. One sec. All right, cool. Here we go. Sorry about that. So, okay, yeah. Now, I'm going to be here giving you just a couple updates, well, maybe a few updates on some projects I've been working on as PyHC's tech lead that all have the overarching goal of unifying our packages and our ecosystem and everything that we do, basically. The first half of this will basically be, I'm going to give you a talk that I gave at IDEA for most people who weren't there. And that's going to be on a new IDEA working group that I've been a part of called the Science Platforms Coordination Working Group. The cool thing we're getting from PyHC there is we're going to be getting a deployment of our PyHC environment, which is exciting. Then I've had two other projects that were both actually ideas back from the summer school that we did, which was making a Python package to simplify the installation of PyHC packages. And I've been working on unifying our read the docs documentation into one hub that has like search across different packages and stuff like that. So I'll talk about those things. I will share how this work that I'm doing with these projects fits into my overall vision of where I'm hoping PyHC will arrive at in the near future. And it's a very pretty vision, I think. Hopefully you'll agree with me, and I'll leave some time to discuss. So here's the part where these are just going to be literally the slides that I did at IDEA, but I'll go through them a little bit more quickly, just so you all can be aware of this new working group and get the sense of what's happening here. So this is the Science Platforms Coordination Working Group, and our goal is to develop international standard software computing environments for heliophysics. And now this is not just a PyHC thing. This is for the field of heliophysics as a whole. But obviously PyHC is going to be a big benefactor here. We're chaired by someone named Jan Rierink, who works over at ESA, and myself. And then the rest of our members are listed over here. You'll recognize a couple of them. A couple of them are in the room also, so hello. And yeah, basically I'll just quickly cover why we exist, what we've done so far. I'll cover the results of a survey that we've been running to inform what we're doing, and then I'll cover the future work, and then I'll move on to other PyHC specific things. So this more or less started, I mean, this has been an ongoing conversation in the field for a while actually, but the getting the ball rolling for this specific IDEA working group started back in Paris in the 23 cloud workshop, where basically people were talking about wanting a shared heliophysics software environment for cloud computing. Just a few months later, in October, I was presenting on my work to basically make this GitHub Actions pipeline thing that Dockerizes an environment with all the PyHC packages and sticks it in Docker Hub. I had no idea what was happening with the conversations in Paris at the time, but it jived nicely with what people were thinking about. And I was told by at least a couple people, including Brian, who was there at the thing. He's our big funding guy and the one who gets mainly the credit for starting this working group, said, hey, we should have a working group on this kind of thing. And I was invited to an email chain where we were discussing these ideas. One thing led to another, and we made an IDEA working group. So the first kickoff meeting for that was October of last year, just right after the first Dash meeting, pretty much. We have been meeting monthly ever since December. So we've had a good number of meetings at this point. And initially we kind of had this idea of creating like one perfect cloud environment where any heliophysicist can go and just do their work in the cloud. But we realized kind of quickly that it was going to be a fool's errand to try to like make everybody happy with one environment. So we decided to go more towards a few different flavors of things. And to gauge what kinds of stuff we think we should be sticking into the environments that we make, we made a survey, which I'll give you a QR code for here. This QR code appears twice more in the talk, and I really hounded on this when I was at IDEA in front of a much bigger group. So hopefully we did get more survey results. I see Rebecca maybe checking our survey results to see if we have more than the 30 that we had before Dash. That would be awesome. That's just a Google form that's asking you for things like, what kinds of work are you doing in your environment and what Python packages do you have installed? But then in the months between February and August, when we created the survey, we were like ideating and deciding what do we do with these things. We realized that we can start testing the deployments before we have the perfect heliophysics environment in existence. So we ran with the HelioCloud base image, and we basically just started going with our different options for deploying the environment using that as a test case. And that brings us to today where we're deploying and iterating. So we have two main partners to do the deployments with. They're 2i2c and ESA Data Labs. I guess maybe a show of hand for anyone in this room. Have you heard of either of them, 2i2c or ESA Data Labs? Well, that's pretty good, actually. 2i2c.org, if you want to check them out. They have a bunch of Binder and Jupyter Hub resources, and their big thing is they recently won a NASA grant where NASA is going to be covering the compute costs to do these things. So that's a big win, and a big reason why we're partnering with them is because now they've got the money to do it. And then Data Labs is datalabs.esa.int if you want to check out their public moderated beta. But they have a bunch of tools in the cloud for scientists to use, and their big thing is they put all of their stuff, I think they're doing an on-prem solution, but they have it all deployed next to all the petabytes of ESA data that exists. So anybody who spins up an environment in ESA Data Labs immediately has free access to petabytes of ESA data, and you can just do science with it right there. And that's obviously a great model because then you don't have to download a bunch of data, you don't have to pay a bunch of egress costs. It's good. So with these two organizations, we have three different ways that we can deploy an environment. 2i2c has Binder and Jupyter Hub resources where there's a small and a big Binder, the small version being like what you're used to on like the free version of Binder. And then there's a bigger one where you have to get an account and you have to join a whitelist, but then it's got much more resources. Their Jupyter Hub thing is fully authenticated, so you have to have a login to use it, but it has like nice drop-down options, so you can pick multiple different environments, and they have different resource options, so you can be using a computer that is much more powerful than your laptop, but in the browser. And then, like I said, ESA Data Labs. One of their tools happens to be a Jupyter Lab just deployed there, and it's connected to ESA's infrastructure. So here's what 2i2c's Binder looks like. It is just Binder. You've seen this before, I'm sure, most of you. So if you have a GitHub, like I've made here, that's the source code for a Docker image, you can just stick the GitHub repo right there into Binder, and then boom, here you go. So this is basically a copy of the HelioCloud base image running in 2i2c's Binder. This is the small version for now, but I've been given access to the big one, so I can do that too. Just a quick screenshot showing a pip list to prove it's got a bunch of stuff pre-installed. Good heliophysics goodies. And it looks the exact same in the ESA Data Labs, except for it's got this lovely European Space Agency banner at the top, and it's connected to a lot more data. I've also deployed this Docker image in a thing called Quay.io, which lets us get pulled into 2i2c's Jupyter Hub, which kind of looks like this. If you watch this little video here where you log in and then you have options to either bring in your own image or you can select from a bunch of different ones in drop-down menus above there. And they all have different resource options. They have like gigabytes of RAM spanning from 12 to 120 gigs. And I think up to like 15 or 16 CPUs was their maximum. So it is possible to get something much more powerful than your computer right there. And this is where I'm saying we're going to be having like 3 flavors of environments to start with. So the HelioCloud base image will be kind of the simplest version. Think of it kind of almost like Google Colab's approach to doing computing in the cloud, where it's not pre-installed with a bunch of stuff, but if you put like, pip install or conda install commands at the very tops of your notebooks, you can run things that way. The PyHC environment will obviously be fully loaded with all the stuff that is currently inside the PyHC environment that I've been Dockerizing but not deploying anywhere. I'm excited to finally stick that on the internet so people can use it without having to know how to use Docker. And then, we'll make one based off the survey results, and that one will try to come more fully featured out of the box and have a lot more things pre-installed is basically the idea. And that segues nicely into the survey results from what we've gotten so far. You know, like I mentioned, we were asking people things like what kinds of work are you doing and what kinds of packages do you have in your environments? On the what kinds of work are you doing front, we've kind of distilled the different kinds of answers we've gotten into 4 main categories here, summarized in this slide, where the main categories of work are data processing and analysis tools, modeling simulations, data fusion and visualization, and software development, maintenance, and data production, which this lines up nicely with the internal use cases we expected to support, so that was good news for us. And then I have this slide, which I know you cannot read because the text is way too small, but it is the top 100 packages by popularity so far. And even with just like 30-ish responses, there were over 1,000 packages uniquely that people were using. So we've got a bit of filtering to do, but more data the better as far as I'm concerned. And we already have some idea of the popularity of these packages so far. And then, yeah, moving forward, we've got basically 4 main pillars of work left to get this off the ground in my mind, which is 1, to just finish gathering survey results, and then obviously build the environment based off those results. We are going to make these things reproducible and citable, which is a really big part of our work. So a big important piece that we want to get right is you should be able to do some work in an environment like this, publish it, and then go cite the exact environment that you use to do the work. And I think that'll be a good win for reproducibility. And once we've got those in place, well, then it's just time to start giving it to people and get feedback, get users, iterate on it, and go from there. And that's pretty much the point of our working group. So this was the thank you slide that I ended off at IDEA. I've got plenty more to talk about here today, but I can take just a quick break. I'm doing okay on time, I believe, and I can just ask, is there any questions on this working group specifically before I continue?
Thanks. Yeah, this is really nice. I think like we've wanted kind of more first-class support for like science platforms for a while on the Helio side. I guess my kind of sort of larger question is, what is the main advantage of moving to the cloud, right? Because obviously there's a big push from NASA and more on the Helio side lately, you know, through things like Helio Cloud and Helio Cloud being, you know, a larger component of things like TOPS.
Yeah.
But what is the main advantage actually being able to work at scale, or is the main advantage not having to install a lot of the software yourself, like having like a ready to go container so you don't have to deal with like installation issues, or is it some mixture of both?
I mean, I would say all the above because I like working in the cloud. The main things we are trying to solve are working at scale is a big one. So when you have huge, enormous, like petabyte-sized data sets, we'd prefer to have people do workflows in the cloud that touch the data there rather than trying to download it and do it on their laptops and stuff. Plus, it just is not practical to do it on a laptop sometimes when you look at the storage space or the compute resources you need. But then with like the PyHC environment, one of the things I'm trying to solve is like the difficulty installing things and just generally giving people one place to coordinate work. Like I think it's a good idea for the field in general to have like a couple different environments where here's the main place. When I'm going to do my day-to-day work, I go to this website and I hit this environment and I do this kind of work. I just, in my mind, it would be a good thing to help promote interoperability and unify our work if we did that. But that's starting to get into philosophy.
Yeah, no, I definitely don't disagree. I would say I think on the sort of scalability aspect, I think we have to think too about like the cloud only is advantageous when it comes to scale if your software that you're using and the data products that you're ingesting are sort of cloud ready, right? So I think that's a consideration. Like just because we have a notebook running in the cloud, it's not by by definition like better than our like laptop or whatever. Though of course, like the point you make about like not having to download stuff, and of course your hard drive size being limited, that is always an advantage for sure. But I think it's just like a larger point. Like I think we should all like in this room be thinking about that, because it's like, especially on the software side, like that's kind of like comes back on us as the developers of those packages.
Totally. Brent, you have one real quick?
Address that.
Quickly, because I am starting to butt against time a little bit.
Yeah, sorry. Yeah, so I'm actually on a HTM grant that it's wrapped up, but we're actually trying to bring cloud awareness to several packages, including SunPy. And so, yeah, would love to discuss that offline with people if they would like to.
Nice. Yeah, so one cool thing about being a part of this working group from PyHC's side is that 2I2C is actually excited for me to get the PyHC environment off the ground and to start getting us and our little community to start using it, because they are looking to go back to NASA to prove what them paying for like ephemeral cloud compute costs is like really buying the community. And 2I2C is hoping to show us off as a good use case. Like, look at what PyHC is doing. They've brought all the PyHC packages into one environment and they're doing X, Y, Z. So you should keep giving us money, NASA. It's like kind of the conversation they're expecting to have and the role they want us to play. So we've got a cool scratch my back, I'll scratch yours kind of relationship going with them. What did I have this? I had this slide which just shows the grant that they won. It was called Ephemeral Interactive Computing for NASA Communities, if you cared to learn about it. I could talk about it specifically if people are curious, but I think I'm going to skip forward to other things. So this is going to be, I'll go through quickly, maybe really quickly, the two side projects I've been working on, which were to bring together PyHC package installation and documentation. So on the installation side of things, there's a new pip installable package called PyHC Core. You can do pip install PyHC Core, and you will get the 7-core PyHC packages installed in your machine. It's pretty straightforward. I had plans to show off pip installing it, but for time, I'm gonna not do that. But I will say there are currently some open issues with this thing. I've done it more as like a proof of concept to show that this kind of idea works. There's for some practical considerations, you should not actually use this yet. Like for one, the Komodo pip install doesn't actually get the Komodo you think. Darren was actually talking about that earlier today. And right now I've started to set up some things that use GitHub Actions to try to run the unit tests for all the packages as a way to verify not only can you install the packages, but they're actually working. But there's some tricky bits in actually running the unit tests because they don't actually come with the packages when you pip install them. Anyway. Yeah. So the reason why I make this kind of thing, besides just to simplify installing the core PyHC packages for things like summer schools in the meantime, is eventually this can grow into something where we have tiered package installs based on like, you know, the package tiering that we plan on doing at PyHC soon with like the gold, silver, bronze and stuff like that. So you could imagine getting to a point to where we can say pip or conda install PyHC and then in brackets either all or gold or silver, and you just get those kinds of things. And then not only does that make it easy for the users who want to install them all in one go, but it also gives us a place to prove, you know, whether or not they're working together. Like if the build breaks because you suddenly can't pip install something because a dependency conflict got introduced, this package can tell us that, which is kind of nice. And then as a documentation hub, I've got a little start to a GitHub project over here, which I literally just started last week, like the day after the election. So not much has happened, but I was able to channel something into productive something. And this is what it looks like right now. It is just a read the docs page that has the 4 core PyHC packages that happen to use read the docs over here. But it does support searching across documentation. And I feel like this is worth showing off enough that I am going to back out of this view and just do a quick live demo. PyHC docs, one second, .readthedocs.io. Boom, so you get to here. And then, this is useful for finding things when you don't know which package the feature lives under. So say like, for example, I have 2 images of the sun and I know I want to difference them, but I don't know what package can do that or where to start. I could go to this documentation hub and I could search difference image. And then boom, what do you know? The documentation to SunPy's difference image function pops up. And then you click this, and then you get to the documentation, but now it's underneath this nice thing. I see a hand going up immediately because I stole your documentation to do this. I had to copy the whole thing. I have not explicitly done anything to not have it be indexed by search engines. Please do that quickly or delete it. Okay. It'll steal that away. Yeah. So we can talk about how to do that stuff properly later, but there is a way for, if anyone who uses Read the Docs right now wants to give me admin access of some sort to your Read the Docs, I can add you as a sub-project to the documentation hub so that your original documentation can be the source of any of the cross-project searching and we don't have to duplicate anything like I've done here. That'd be cool. Cool, sounds good. But anyway, so that exists. And then there, I went through a demo there. So here's the part where I'm gonna be standing on my soapbox to give my vision of how this all ties it together into one unified thing. I do sort of wish I had more time. I'm scheduled to end at 3:05 and it's 3:01 here. So I guess I'll go through this quickly and maybe there won't be enough of as much of a discussion as I was hoping, but yeah. But this slide right here pretty much summarizes where I'm trying to get PyHC to in the near future, which I'm defining as within like by this time next year, or maybe within 2 years from now if some things go really slowly. I'm pretty happy with how I did this slide. Actually, it's pretty slick because I can click any box here and then I can click this to go back and it's this fun little gridded thingy so I can explain all the different parts of my vision. But in a nutshell, it's got 9 core pieces, which when I think puts together makes a really unified and well-oiled machine that I think more or less lives up to the mission statement that we've been, parading around with since we formed in 2018. And the first step here, I think, is having that PyHC environment, a place that has all of the PyHC packages installed, ideally next to all the science data we could ever need, and in a citable format so you can do any kind of workflow in there and get a DOI for whatever kind of work you did. That already is a huge thing, just having all of our packages working together in one place. The gallery has been an afterthought, I think, for a long time, and I have plans to revive that, not through a renewed effort of please everybody submit examples to the gallery, for God's sake, we need examples, but I'm gonna actually scrape everything just automatically from the documentation because everyone's got great examples in their own documentation of how to use their packages, and I can think of a number of different ways to like web scrape those and put them together in one spot so that we can just automatically update the gallery as people update the examples in their own documentation. And then I can use the PyHC environment to actually run the gallery examples. So it's not just code that you're looking at, but it's actually like cells in a notebook or something that you can even play with if you feel like, which is nice. Having pip and conda installs through stuff like the PyHC core package I just demoed off, I think will unify things, giving us tiered installs, and something that I've been promising for a while and that is in the works, at least now, or at least in the concept stage, is hiring a student intern whose whole job is basically just going to be to like help people get stuff into conda if they feel like that's too hard for them. We want a PyHC developer. If we get even just a student, it's a simple enough job that they can do that. read the docs, unified search across documentation like I already showed off. The PyHC chat AI bot, I think, pulls all of this together, but I'm really bullish on AI stuff in general, so I'll circle back around to that one. But we've got the heliophysics software search interface that I think we're hearing about next, actually, after the break. So you'll hear more about that, but that's for people who would prefer a more traditional search interface on a website rather than talking to a chatbot for everything. And then stuff you already know about, like summer schools for in-person learning. People like that format, so keep doing it. Standards will continue being at the heart of everything that we do, but we also plan on having a developer around to actually give you dedicated help to live up to those standards. So like actually solving GitHub issues for you, or like actually contributing code, just giving you a free worker kind of. And then PyOpenSci for quality peer reviews and just getting that done in general. I'm at 3:05, but I've been blessed to go 5 minutes over. So thank you for that. I could talk for a long time about what PyHC chat can do to bring together this whole thing. But I think for a moment, if you just picture that all of these things exist, imagine going to a PyHC environment where you have all the packages and the data and blah, blah, blah. You could look through a gallery of examples if you want to figure out what's going on. You could read the documentation, or you could search through a search interface, or because Jupyter AI exists now. There's an extension for Jupyter Lab where you can put a large language model chatbot just right there in the left side pane, and you can have it interact with notebook cells and whatnot. Well, boom, I stick PyHC chat, a chatbot that is an expert on every PyHC package and every single fact about PyHC in an environment that has all the PyHC packages. Imagine what you can start doing. You know, you can ask, how do I solve X science problem? And it'll start writing the code right there for you in a notebook cell where you can run it. You can say, I want to write a paper on this. Help me understand my research first. And it starts writing the prose in the thing. And maybe after an afternoon of hanging out with your chatbot friend and writing some code and writing some stuff, you might have the beginnings of an executable paper that you could already have a DOI for and ship it off to publishing. Like, AI gets you a lot in this space, and I'm hoping that by tying it in with the environment and all these other things, I'll get one step closer to my vision of PyHC chat being a one-stop shop tool to help you do research, write code and papers and all that other good stuff. And yeah, I could drone on and on, but hopefully people are starting to see how like these are all very great things to have, and I'm just here to tell you today that I'm working on every single one of them in some capacity, and I'm hoping by this time next year to be able to stand in front of you and more or less show this same slide and point to the fact that we'll have it all. If my grants go through and if the work isn't harder than we think, should be doable in a year, but we'll see. And I think I'll stop there.
Okay, I know you have a couple things in Slack. I can read it out louder if you want to read it and then answer.
Let's see here. Could you say it out loud just so
Yeah,
people
I can do that.
can hear it?
Yeah. I see your comment, Stuart. Brent, given the original goal to make an all-in-one environment for heliophysics researchers, how are you deciding what makes the current environment's images, and or what would be making it in this environment or image at all?
Yep. So the first clarification point on that one was that we are going to be making multiple different versions of environments. We're not going to try to have one that has everything. But to quickly run through the three that we're having to start with, we're using HelioCloud's base image as the most basic, like almost nothing heliophysics specific installed except for like the basic compilers and things that you normally need. The PyHC environment will have a bunch of PyHC relevant things. And then we've been running that survey on just general what are heliophysicists using on their computers to try to get a more informed look of what the field looks like and hopefully try to make one environment that comes pre-installed with a lot more things that you would expect to need. But that'll be like the big bloated one with a bunch of crap.
Cool. All right. There's one more question in Slack. I guess kind of two follow-ons. So is there a guide how to create and contribute to the PyHC gallery? The repository has no forks. Also, any suggestions on how to make an arbitrary PyHC package friendly to PyHC vision search, documentation, and AI chat?
Yep. There is not much documentation on how to get how to get gallery examples out there now. And in fact, there are actually two different versions of the gallery. So there are instructions that are kind of difficult for one older version. The newer version, it's as simple as you just submit a notebook to this GitHub repo that we have for it. But at the moment, I'm forgetting where those instructions are. So my apologies if they were not easy to find. But if you do go to the old version of the gallery, there's a link to the new one at the top. Like it says, try the new version here. And then the second question, I'm forgetting the second half of the question. Tell me again.
Any suggestions on how to make an arbitrary PyHC package friendly to this PyHC vision search documentation AI?
Oh, certainly. The easiest thing is just if you use read the docs for your documentation, that this will for free work with any documentation that uses read the docs. If it's Sphinx, but not specifically read the docs, I can still pull it in. Otherwise, if it uses anything else, it is currently not compatible with the documentation hub. And I might go down the rabbit hole of doing some kind of hack to pull in other kinds of documentation, or I might just make the cutoff there and say, if you're not using Sphinx or read the docs, you're just not a part of this. We'll see. I just started doing that like prototype a few days ago.
Yeah, I just had a question about the PyHC like gallery or like meta gallery, I guess. Yeah, so I think it's a good idea to like just like most people probably use like Sphinx gallery, I would suspect. So you presumably you could just like link to or maybe scrape. I don't know what the right way to do this, but so the way you described it is then you would run the other people's gallery examples as well, or I'm just confused about how exactly that would work, or would it just be like linking to those existing?
Oh, certainly, yeah. Well, part of the reason you're confused is because it doesn't exist yet, and I'm just basically throwing my hands around and saying, I think I can do this, so I'm planning on doing this. But the way I envision doing it is doing some kind of web scraping, probably with an LLM, actually, to have some smarts behind what it's scraping and what it's putting in. And I want to pull it into notebooks, basically. So the idea would be like, go look at a documentation website, find every code example that you have in there that's an example in the documentation, extract the code, stick it in notebook cells, and then have it runnable that way.
Oh, so you're talking about not just limited to like Sphinx gallery.
No, I'm talking about extracting examples from a Sphinx gallery documentation page and sticking it somewhere where it's actually runnable.
I see. Okay.
Yeah.
Thanks.
Cool. Any final questions? Double checking Zoom.
All right. Well, thanks for letting me steal 7 minutes of the break there.
All good. All right. Let's see. We are scheduled to come back at 1:30. I think I can probably make my presentation a little shorter though. So come back at 1:35, save a few minutes. Or sorry, not 3:35. Whatever the next 35 is, come back at that. Sorry, I was looking at the number 13 at the same time. And anyway, 35, come back at 35. Okay, that was a shorter break. It's time to start, and it's with me, so I'm just going to power through. Okay, so the next session coming up after this talk is kind of digging into the metadata side of the HSSI. So I thought it fitting, in case there are people in the audience that didn't know much about the HSSI and what it is, to give a quick little introduction into it. Actually, before I go to that slide, I'll preface this with the HSSI stands for a Heliophysics Software Search Interface, and this was a NASA ROSES HPOS high priority open source science funding that I was awarded as of like October of this year. So very new, very recent. And you might have seen a young undergraduate student in the back earlier. He had to leave for class, but that's Isaiah Smith, the student who will be working with us on this effort. So the HSSI, why we decided that this is something that we needed. Really, it kind of started as a little grassroots convo. I think it was me, Rebecca, and Brian, just hallway sidebar conversation. But generally, generic search interfaces, think of like GitHub, Google, that kind of thing, as we all know, don't really provide science-specific filters so that we can search more specifically for the kinds of things we're interested in. The ADS, the interface links there are really based on software citations, which are noticeably absent from a lot of heliophysics publications, although, of course, now that everyone's thinking about it, it's getting better, but still. And there's also no current resource that really helps with the discoverability part of things. So if you know what you're looking for, you can Google it and probably find it. But if you don't know what you need, it becomes a lot harder. So the HSSI is trying to help with that effort. As for why what we already have in Helio so far isn't sufficient, the PyHC search interface, as we all know, has just Python in it. And it doesn't cover a lot of different software in different categories. We don't have a ton in the way of AI/ML, models, simulations, that kind of thing. There's a general need to align with metadata structure with the heliophysics world's needs, as well as international standards, to make sure that we're connecting with the wider community. And then there's a lack of links to other important resources like other related software, data sets that can be used with your software and so forth. As for why software.nasa.gov is not sufficient, there are many reasons. But the existing science software funded by NASA is not always covered. If you look through this list too, you don't see a specific Helio category in there, which is concerning. But there's also not really an AI/ML category here, post-processing, that kind of thing. It's also not linked to the ADS or SciEx, which is commonly used in our field and in Astro, the sister field, if you will. It's not linked to data sets. Like I mentioned, there's a lack of representation of heliophysics-specific software and a lack of community awareness. So this was a slide that I think Rebecca sent to me. It's a screenshot from someone's presentation at the NASA SMD software workshop back in May, I think it was 24. I had never heard of it until that workshop, so there's that. So the HSSI, many big, goals proposed here. We want to unify software metadata with code meta recommendations in international organization that many, fields are adopting. So we want to work better in that sense. Improve, obviously, software search capabilities and simplify citation of software and other resources. It's really meant to be kind of a one-stop shop for finding software in heliophysics. So the tie to PyHC is we're going to be starting with first, bringing in all the PyHC packages and getting that integrated as step number one. And that's a lot of what Isaiah is going to be working on. He'll be the main person creating the HSSI, content with Mayan and Sean's help, of course, as well as our metadata experts and so forth. And then the goal is to then expand out to heliophysics code in other programming languages, because we are not only Python as much as we'd love to be, and then also work to include software in other categories. We'll also be, there we go, creating interoperable software metadata. So we're going to be working on making a new software metadata structure for our software registration for Helio, and then build a registry of software metadata with a REST API on it. And of course, we're really trying to not just make this in a vacuum. So we're sourcing input from community meetings. So that's going to be happening shortly after my talk today. And then there's another afternoon session tomorrow to further that effort. I'm not going to spend too much time on this, but just to say we have our core team. We've got metadata folks working with us, Rebecca, Catherine, who I'm sure will be back soon, Joe Renault from the EMAC team has also been helping with that. I need to add his name there. And as I mentioned, there will be some EMAC folks, which you'll hear about in a second what that is. Starting here. So the software search design, we're basing it on things that already exist. So reuse of software and trying not to reinvent the wheel. We have obviously the PyHC, site where we can pull some of those keywords and all of our packages in. But as far as functionality, looks, all of that, we're going to be leveraging EMAC, or the Exoplanet Modeling and Analysis Center, and how they've set up how they do their search interface in exoplanet research, because it turns out it works really well. It's highly adopted by the community, and they've already thought of a lot of the problems that we would want to solve. And of course, there's, bringing in the software, nasa.gov, ADS, Zenodo ideas, and so forth. Couple upcoming sessions, the ones I've mentioned here that we'll have at our fall meeting. And then also, if you are going to AGU, there's a couple different posters that will at least mention this. So Catherine is going to have a poster for the metadata structure in the PyHC poster session Thursday afternoon. And then I'm sure somewhere on my poster here, I haven't put it together yet, but I'll be mentioning the HSSI more generally and broadly in my poster that I've got there. So as a summary for this quick blazing overview of the HSSI, the goal obviously is to significantly improve FAIR for research software in heliophysics. The NASA ROSE's proposal has officially been awarded, and we're already underway getting work done on that. Initial work between PyHC, the EMAC folks, and HDRL is progressing nicely. The metadata framework is now ready for more detailed efforts, and we're going to be digging into that in the sessions that Rebecca, Catherine, and Joe are leading. We're going to be looking for collaborations with various international communities in the software metadata area and getting feedback from y'all. There will be those dedicated sessions I talked about. And of course, most importantly, we don't have a logo yet, so we're going to be thinking about that. And that's what I have for you now. Any questions?
So if this should be deferred to our conversations later, then please say so. But this is great. I really like the connecting out to other things, data sets, papers, et cetera, et cetera. What are we going to kill? Because the number of things that we are trying to add to is growing. And so, are we going to ditch the PyHC project list and just make that a checkbox on HISI and then kind of leverage that? What do we do about the existence of the SPACE software metadata? And this looks good. I think this is much more ambitious, has a much better idea, but we still have these other things rattling around that, how do we avoid the XKCD problem?
We're not killing the PyHC site, our project listing site. I'm going to start there. I feel like there's benefits to still having our project listing, especially once we do these tierings and we can talk about all the different things that these offer, as opposed to just here's a listing of software and where you can go get it. Like, that doesn't tell you much about the robustness or quality of the package itself, just that it exists and you can find it. Well, I mean, the tiering is going to be based on Python-centric things to start with, and the HSSI is intended to be bigger than that. Rebecca. Sean, can you give Rebecca the mic?
So tiering is beyond the scope of a software search interface. It implies that you're implying standards on development across a large range and types of packages. Developing standards in those other languages and those other application categories is going to be a long process. And those standards that they develop should probably stay within those communities.
There's that. What was the second half of your question again? Sorry. Space. Do you want to talk to that? Or?
let's have a discussion over lunch or dinner, whatever meal is next.
We have a dinner tomorrow night at Rio, so we should talk further about that, but we have reasons why we have not leveraged space. Are there any other questions or thoughts?
So given that there's the software.nasa.gov and there's the PyHC website and, you know, the catalog and everything like that, where would this search live?
So it's not a part of the PyHC site itself. It would be its own entity. I don't intend it to necessarily be soaked up by software.nasa.gov or by PyHC. It's bigger than PyHC and it's bigger than software.nasa.gov.
Right, but I'm saying, would it be associated with PyHC as an organization or nasa.gov or anything like that?
I was going to say it's technically separate from all that. It's its own thing.
So it'd have its own website. Okay.
Yes, that is the answer. Was there anything in Slack? Because I'm not looking at that right now. Sean, can you read out whatever's on Slack?
Yep. How are you defining software? A recent push to lump simulation models as just software is misguided.
Per SPD 41A, that is actually considered software, so that's my official answer to that question. But we are not trying to be the one-stop shop for all things modeling, where it makes sense to include, you know, those kind of components in the HSSI to list if people find it useful. That would be cool. We'd obviously work with the modeling community to make sure that the metadata, you know, registration we have for that makes sense. But yeah, that's my short TLDR. Were there any others? Okay. I'm going to yield the floor then to the follow-up to this, which will be Catherine's, I believe, presentation. You know where to find me if you have more questions. I'm ready.
Gosh. Oh, yep. Wrong one, wrong one.
One more second. Where are you? What'd you call
it? It's HSS. Okay, my name is Catherine Bird. I am the digital librarian for the Heliophysics Digital Resource Library. Also, from this point on, we'll be referring to it as HDRL because I'm not going to say that whole thing. And that's at NASA Goddard Space Flight Center. I will be talking today about the creation of a heliophysics-specific software search interface regarding the metadata structure and the controlled vocabulary. And the HDRL is leading the effort for the creation of the metadata structure for the heliophysics software search interface, which I will also now be referring to as HSSI because I'm not going to say that whole thing. So HSSI will apply to all the programming languages. It will align with schema.org methods, and it will further align with international guidelines from the Code Metadata Project. This is what we're trying to piece together to be the structure of the HSSI metadata fields. We've been working with NASA's Exoplanet Modeling and Analysis Center, also known as EMAC. We've been working with their current software search interface as a starting point instead of just trying to reinvent the wheel. Because why would you want to do that? So why did we choose Code Meta? The Code Meta project is an internationally structured for software metadata, and it's primarily based on schema.org, which is the structure, which is a generic structure for internet search engine use. Code metadata contains crosswalks to several other metadata structures, including GitHub. So that's been useful. Code meta enables auto inclusion of HSSI listed software in a future international software search interface, allowing it to evolve as needed. So you can get a little snapshot of that visual. HSSI metadata registry will be hosted on GitHub with REST API and will be routinely archived with Zenodo. As I mentioned a moment ago, we've been, I think I mentioned it. Yeah, we've been working with PyHC and EMAC, their existing software metadata structures as a starting point. We know we need to incorporate international recommendations, which you can see listed on bullet 3. Yeah, you can see that listed there, the recommendations, as well as requiring mapping to common software structures listed on bullet 4 right there. So we've generated several use cases for HSSI based off of EMAC and PyHC search interfaces and their experiences with it. Additionally, we've completed a study of what controlled vocabularies are needed, and these terms have been mapped to Code Meta, DataCite, and schema.org. Over several discussions we've drafted which metadata fields would be classified as mandatory, recommended, or optional. Though I'm assuming you missed it, but you may recall from Julie's presentation that the more metadata fields you include, it leads to a higher ranking of searchability and visibility to find what you're maybe looking for. And come to Rebecca Ringet's talk tomorrow to learn more about that, provide feedback. So use case summaries. we have come up with several, about around 30 different use cases for HSSI. As I mentioned earlier, we've already said that. So here's a brief summary of some of the more important, or rather most relevant use cases that you can see listed here. Application type and functionality will be the main focus to be discussed later on. And this is a screenshot of a spreadsheet when I say we, I mean me, Rebecca, EMAC, and LASP, and NASA. We've collectively been working on this to determine the importance of each metadata field, including which fields will be presented as like on this first column, like a function, what will be a button, like to make it more accessible easily, and then versus things that are maybe not as high of importance that could be a text search field. So this is a mirror board that is a lot on there. Essentially, but what's important to understand about this mapping is that, so obviously there's a lot of boxes going on here. So what really matters is the lightest yellow ones are the top level name of fields in data site 4.5. The golden, more like that color, the golden ones are second level fields that we found in data site 4.5. And the orange squares are third and fourth level metadata fields that we found in data site 4.5. The green squares are concepts we've selected for HSSI metadata, and some of them are different than what data site has listed. That's why you'll see a majority of them kind of clustered together away from the other box squares. That's really all we don't need to go through all that. So our automation plans are to harvest metadata from GitHub and Zenodo, including the metadata fields listed below on this, you can see for yourself. And you can see in that screenshot that we've been utilizing the code meta project to harvest these metadata fields to generate what's the most relevant fields for HSSI. And here's a list of controlled vocabularies that we've determined to be relevant to HSSI. The top two, application category and software functionality or functionality list, they're bolded because those are probably two of the most important relevant parts of that. And we're looking for feedback from the community. We want your feedback on application category. We're interested in what application categories would be relevant to heliophysics, such as software application categories that may not currently be in PyHC. So there is a QR code and a link to a Google survey, which we'll go over in a bit to discuss if there's like a consensus of certain things that you guys would like to see or people of the community would like to see. Oh. Yeah. Excuse me. And additionally, we want your feedback on software functionality, the primary functionalities of the softwares, or softwares, whichever. And then to the right, you can see sample terms sourced from PyHC, EMAC, and NASA on the right side. The current plan is to is a drop-down menu with some sort of text search to find the right thing, like what you're trying to find. And again, we're interested in what software functionalities are related to heliophysics, including software functionalities that might not, again, currently be in PyHC. So there is also another QR code. It's going to take you to a Google survey, which you can hopefully. Did I miss one? I missed one. Yeah, that one. Give it a minute. Sorry, I moved fast. Yeah, like go, like please, like, and then I'll even, well, yeah, I was gonna show what it would look like, but I'll just kind of talk through it actually. So we have listed things that you can, select as many, once you get to the Google survey, you can select as many that you think are relevant. And then there's a option for other, and we would like for you to type in what that other would be if you have something that we didn't list. And then further down at the bottom is the option for none. So on. Okay, hopefully that's given everyone enough time to get that. And then this is, nope, nope. Oh, right here, this is, okay, so pause for discussion, okay. I'll give you guys a couple minutes to kind of do your thoughts. Oh, maybe that was that one. It's the application category. Yeah. Okay. Oops. already seen some consensus on certain ones, which is what we wanted.
Yes. Mic check. All right, great. So comparing answers from the two, the second one is asking what should be removed from our list, basically, and the first one was asking what you have seen. And I'm seeing conflict already, and I want to ask questions of the group. So what I'm showing is answers on the second question. It's not unanimous consent, but a lot of people are saying that, for instance, a Sparkle endpoint should not be on our list. And I'm interested. That's the first question. Yes.
I'm sorry.
So that's okay. So I want to hear about the two examples where you have used a Sparkle endpoint in heliophysics. Would either of those two people like to tell us a story about this to help us understand how we should treat this in our system?
I'll clarify that I was one of those people, but I didn't do this for heliophysics, so I think I'm going to remove myself.
Okay. It should be in heliophysics. Okay, not hearing any responses. I'm not watching Slack though. Okay. All right. So fairly normal. I'll avoid the math word. Fairly usual or expected distribution of these things. Okay. Visualization package, surprised that's a little bit low. Not surprised at Jupyter Notebook being pretty high, script being high, web or cloud application, all of those things are kind of as expected. Now things to remove. Still really interested to hear from the one that indicated they used a sparkle import in heliophysics. I want to hear that story. No, I'm not joking. Like I know of examples in heliophysics. I just want to hear enough motivation to keep it on the list. So I need to understand that story. That's not a joke. I'm not poking fun at all. Okay. Otherwise, I mean, there's comparisons we can do offline. But if you haven't had time to quite finish this, I figure we give it 1 or 2 more minutes, and then we can move on to the next activity. The questions are going to be almost the same, but the answers will be extremely different and longer, unfortunately. But the point of this is so you can help us call down these lists to be things that people would actually have programs in those that satisfy that terminology in the interface. And so that we don't have a long list of things that half of which are irrelevant to most of it. Yeah. So the things on question 1 that are getting a lot of responses are probably going to wind up in our top 5 lists on the search interface. Like those will be the buttons or boxes you can check that'll be visible, and the other things would be you'd have to click to drop down and see more options. Visualization package, Mike. We'll have to talk. All right, are you ready to move on to the next thing? Yeah. Does anyone want another minute or 2 on this? Let's rock and roll. Here.
Wait, my God.
So I'm sharing the screen. I need to stop.
Okay, yeah.
And then you steal it back.
Okay.
I'll just say.
I get
this one set up.
Wait, how do I find this? Google? Oh, okay. Okay. Additionally, we want your feedback on software functionality, the primary functionalities of the software, Helios physics specific software. To the right is a list of sample terms that we've sourced from PyHC, EMAC, and NASA. Our current plan is to do a drop-down menu with some sort of text search to find the right thing you're looking for. And again, we're interested in what software functionalities are relevant to heliophysics, including the software functionalities that might not currently be in PyHC. And there's the QR code for that Google survey. Yeah. Yeah, because we're looking really for like a consensus to what the community thinks is the most relevant. So I'll give you guys a couple minutes.
Okay, seen a lot of good responses. I want to ask questions about this low end of percentages on the first question for this one. I want to understand what that actually is. So for example, the electronics and electrical power, one person indicated that. Can you tell me a little bit about what that was in heliophysics? Yeah.
When I started on the Themis mission, I did a lot of electronic ground support equipment and design software. So that feels like it fit. Restricted? I don't think so.
Yeah, we intend to support restricted software on the HSSI. It's just the access URL will be a little bit different, obviously. The other one, radiative transfer tools. I'm happy to see that. Can I have a little more understanding on what that is? Is it someone online? Can you tell me a little bit about that?
Yeah, that was a chromospheric modeling code. So like predicting the spectrum of the chromosphere based on like what the chromospheric structure was.
Great, great. That's good. I have a question I might regret asking, but like for example, we separated data visualization into 5 things here. So we could either do that on the interface as in data visualization and you pick which subcategory, or we can just loop it all into data visualization. So are there any strong opinions for or against just looping everything into data visualization versus splitting it up?
Yeah. So some of that is actually the code itself is the data visualization, but then sometimes there is tools that use data visualizations as an interface. And so I think there's a difference there that is very clear.
Can you give an example of each?
Like PyTplot and then PySpeedS. Like it uses PyTplot, but it's going to wrap it. Eventually it will integrate it, but it's the thing of it. They are separate right now.
Okay.
Well, as I'm bringing the mic over, I'll give my opinion too, which was if I were doing this in a search interface and I was looking for software that did data visualization, I would want to be able to check just, I'm curious about all kinds of data visualization, and in one checkbox include the 2D and the 3D and all the other subtypes.
So I'm going to totally agree with you and then say the thing that I was thinking before, which is totally contradictory, and I also still believe so much stuff does visualization in some form or another. And if it all is listed under D, I mean, like this right here is perfect example, right? If you gave me this interface, I could not actually like, right? And so I think it's important to be able to do a fine-grained search, even if it's important to be able to easily find everything. But it also, if we can think of a more descriptive way to say it than data visualization A, data visualization B, right? And it's not easy, but I think there needs to be some granularity there. Yeah. Because I think in some cases people will be thinking in terms of, oh gosh, I've just got to think of anything I can throw at my data to try to look at it in a weird way. And other cases, people might be thinking much more application specific, which other fields might help in drilling down, but.
You could also consider web-based visualizations in this as another category, because think about bokeh, those types of things, but it still builds off of matplotlib, which is not necessarily would be listed here, as it's not specific to heliophysics.
Can you email me that idea?
Sure.
Web-based visualization category. Perfect.
Yeah,
Catherine's got it.
I have several in my mind that would fall under that category too, but they're not heliospheric specific.
If you use it in heliophysics,
Yes.
that's the thing we're
Yeah.
looking for. Yeah, perfect. Are there any other things, any other categories here that you think are fuzzy enough to warrant a subcategory approach to it? Write down your list and put them in Slack. Because I know there are probably at least 5 or something like that. Particularly interested in examples on subcategories such as models and simulations, model fitting tools, poke, Darren. That would really help. Not that we're trying to go fine-grained in any of these categories, but enough for someone to find a digestible list. As in not 30 options, but maybe more like 10. You need a mic. Sean, you need the mic. Agnes, give me one.
Like actually, I tend to hold the microphone up. So in terms of model fitting, the place where I've been using and developing that most often is forward fitting models to data. Dust impact modeling for IDEX, and just some forward modeling of a distribution function through an instrument response, that kind of thing. That's where most common using it. So that's quite different than like doing things with the output of global MHD models.
What category name would you propose?
No clue. But I think some sort of line between doing stuff with output of, primarily physics-based models and data assimilation and that kind of forward modeling through a response function, those are all related, but need to be distinct in some way.
Okay.
So instrument response modeling might be a category.
That's a good one. Instrument response modeling. That's closer to mission than actual physics modeling. There's both, right?
Yeah. We're having that argument with IDEX, actually.
Oh no, I won't get into it. Okay.
There's a whole spectrum of tools that fit this category. So it could be as simple as taking a scatter plot and fitting a line to it, right? So, or it can be a huge model like Weimer that just takes decades of data and works it into a categorized prediction, right? So there's a whole gamut of tools that could fit under that word.
So maybe empirical under the modeling category, maybe forecasting could be a category, MHD, physics-based. Some things will overlap. We're not trying to be distinct between them. You just click more boxes when you submit your package.
Yeah, I don't have a clear idea of what to call it. I'm just saying there's a wide gamut, and it will be tricky to see where things fall in which categories. But obviously, you make a first stab at it, and we can finesse things in and out of categories as we go, I'm sure.
Yeah. You're exposed to a lot of models there at CCMC. Could you possibly run off, say, 5 broad categories most of the models there would fit into?
Well, you're going to have first principles physics models. That's going to be a big category of it. You're going to do something, well, something like a Weimer, which is like it's not data assimilation going forward. It's categorizing decades of data into something as a model. There's some models use data to guide what they do with it. You know, Amy takes observations and pulls it in together and pushes out something that's guided. There's data guided, there's data assimilated, there's first principles physics, there's probably more. I'm just not drawing a blank right now on what other categories to call them.
Okay, we could put that in this thread on Slack later and tag me on it or tag Catherine on it or both, whatever you want. That would be quite helpful. But we're not looking for like 15 categories. We're looking for 5, maybe 7 that most things would fit into, and then everything else would be an other box. We're not trying to replace a search interface for model specifically. That's not the scope here. It's, can I get to something that's roughly around the thing that I want without knowing the name? That was a problem that came out in the Jack Eddy workshop last year around this time, even with the CCMC interface, unfortunately. But trying to get people kind of in the rough area with some initial things to look at. That's where this is coming in. It's one use case here. But yeah, any other ideas? Throw it in this thread on the Slack, tag Catherine or I on it. My email is easy to find, so is Catherine's. We work at Goddard, so just search our names with NASA Goddard and you'll find us. I think that's enough time. Do you have anything?
So Joe had a comment in Slack. Question for the room. Rebecca, you mentioned tools that are used by heliophysics versus built for. Where do we draw that line though, before we try to list Notepad and Mac OS on HSSI?
Have to figure that out, won't we? I don't intend on listing operating systems on the search interface. I think that's a really good no. What they depend on, yes, but like what operating system a given package depends on, yes. Right. But
Sorry. And to go along with that, like, where would this fit in given the larger Python community and all the packages on PI?
how easy have you found it? Pardon my lack of English today. My understanding is that it's hard to find something on PyPy unless you already know the name of it. That's the point of this. We're not looking to cover all of Python. We're looking to cover vast majority of heliophysics. So, which includes a lot of software that's not in Python, and it never will be for a variety of reasons. Hopefully IDL is a thing of the past sometime in the future, but just echoing Brian's sentiment there. Where does it fall compared to PyPy? This is a search interface. We don't store software. We store the metadata for it. And the links from a given result will give you links to PyPy or Conda, the GitHub repository, all those things. Heard something on Slack? I think I can stop sharing.
Joe further clarified. I guess my question would be, is anyone using HSSI to find NumPy or to find what tools use NumPy, that kind of thing?
I didn't hear it all.
Or to find what tools use NumPy?
That structure is in the metadata structure. That field is in the metadata structure. So we're planning on having piping in from GitHub all of the software dependencies for a given package. So if you wanted to search for, okay, what packages use NumPy, the list will be insanely long, but it should be able to give it to you. Same thing for AstroPy, because I know that's going to come up. Yeah, just kidding.
So it sounds like you'll be able to search dependencies that aren't actually in HSSI, right? So if you're saying you're pulling all the dependencies in from GitHub, that means I can find stuff that's in HSSI based on dependencies that aren't.
Yes, I think.
Okay. So it maybe seems reasonable to say that the line should be, is a heliophysics researcher going to interact directly with it? People are going to interact directly with NumPy. People probably aren't going to interact directly with Atlas or BLAS.
I haven't heard of those.
See? But you use them every time you use NumPy.
I think that's it.
Thank you guys for your
Thank you all for your feedback. It was very much appreciated and will be very useful for us.
Okay, we can wrap a little early today. I'm sure no one's upset about that, but I also, before we leave, wanted to open it up if there were questions or thoughts from anything from today that you didn't get a chance to say. There's time. Or we can just go home. Okay, let's just go home. All right, cool. We'll start at 9 tomorrow, same place. Thanks, everyone. See you there. Sleep well.